into the place where it goes in a kernel. So again, careful management of which type information we're sure to know gives us silent splicing of computed kernel designs into position. Okay, so that's my second adventure, and I'm still remarkably on time. So yeah, so I want to talk a bit about what's going on in these brat function types. I promised you a bit of dependency, and now it's going to show up. We certainly want to be able to write polymorphic functions, but we're also interested in being reasonably tight about the sizes of things. So at the moment, we are allowing a limited form of dependency on values that live in kinds rather than types. So there's a type-kind separation. Kinds are types of types. Sooner or later, everything will be a kind, and then we can just throw the types away. But for the time being, we have kinds, and we are careful to distinguish parameterized brat types. So star is the kind of brat types, from dollar, which is the kind of kernel types. The dollar is to indicate that there might be some sort of resource involved. And then we've got hash, which is the kind of numbers. And because we're very careful to do kind checking rather than kind synthesis, we can overload type constructors that might make sense in different ways depending on whether they're supposed to be constructing a brat type or a kernel type. And in particular, vectors preserve the world they live in. You know, brat vectors have brat elements, kernel vectors have kernel elements, but they also have a length. So that means we've got a type-level notion of length, which also, so type-level lengths also have to exist at runtime. They have to be runtime values, but we need to figure out how the type system copes with them. So here's a fun puzzle. What's just happened? Oh, we're stuck. I turn the page, and it's only happened once. Have I done something? It's them. Okay. I don't think it's... Okay, but we're upside down. We'll be back in a minute. Anyway, so the puzzle, I can do this is a wordy slide, is how to design the language of lengths, of numbers that show up in types in order not to have a miserable time. I mean, of course, there are all sorts of fantastic things you can do with numbers. And if you want to manage a type system with kind of arbitrary numerical expressions in them, well, good luck to you. You might, send all the constraints to a SAT solver and hope. Or you might kind of do arbitrarily large amounts of theorem proving. As ever, my inclination is to say, well, what can we manage without switching on any of that heavy machinery just by being neat? So clue number one, these numbers aren't general purpose numbers. They're intended to explain how things scale up. So we would quite like our functions to be monotone and boring. Right, another perhaps controversial suggestion is that the great simplification can be achieved if you have the good fortune to be able to use structure instead of arithmetic. Now, we don't know if we'll get away with this forever, but we're certainly going to try. So if, instead of having a vector of two lengths added together, you can keep that as a pair of vectors, or instead of doing multiplication of lengths of vectors, you just have a matrix, then you are down to functions in one variable. So that's a significant simplification. And then finally, the real clue is to think, well, we're going to use these numbers for lengths of vectors primarily. So the way we want to take the vectors apart tells us, repeatedly, tells us the ways we want to put the numbers together. So how do we want to take the vectors apart? So I kind of cooked up some hand-waving notational possibilities for how to take vectors apart. We might want to check whether a vector is empty. That means we need to represent lengths of 0. We might want to take a single element off the start or off the end. So we need successor. And by the way, as anyone who has ever taught functional programming to undergraduates knows from the amount of confusion they found in the room, the decision to use a symmetrical symbol for the non-symmetric cons operation has questionable virtue. So I like to put the commas at the ends where the single elements are, and sort of something horizontal where we're expecting 0 or more things. Right, so then this thing is for splitting an even length vector in half. So the equal signs are meant to suggest that what's on either side have the same length. So that means we need doubling. And then, so if you've got an odd length, it's very easy to take one off the start and chop the rest in half, or off the end and chop the rest in half, but it's perfectly sensible to want to fish the thing out of the middle of a vector of odd length, so we'll need a thing for that. And that means we need 1 plus double. And then this other gadget, of course, you might want to, instead of halving and chopping, having a beginning and an end, you might want to deal out the things in even and odd positions. So that's to say, paying attention to the least significant bit rather than the most significant bit. So again, that needs doubling. And of course, if we're going to double repeatedly, if we're doing a kind of divide and conquer, split the problem in half scheme, then we're going to need exponentiation. So my first attempt at a language of type-level numbers is this one, numerical expressions. I've got a single variable, I've got 0, and I've got a bunch of ways to make bigger, which is 1 plus 2 times and 2 to the power. And I've got some equations that explain how doubling and exponentiation compute. But then the point is, I need to be able to work backwards. To do my pattern matching, I need to ask, are you 0 or successor of something? I need to ask, are you even or odd, and what's your rounded down half? Okay, so the good news is that 2 to the power is really easy to tell even from odd. Because we can tell, 2 to the power of something is odd or even accordingly as the something is 0 or successor. And if we've made sure we can always tell 0 apart from successor, then job done. But the nuisance is answering 0 or successor for 2 to the power. Right, well, the easy bit is that it's always a successor. The hard bit is what it's the successor of. Can we explain how to deliver the predecessor in this language? Well, it's pretty tricky because it's 1 plus 2 times the predecessor of the previous power, which means the numbers have got smaller, but the problem hasn't. We still need 2 to the something minus 1, and we haven't got it. So, brainwave, if you can't fix it, feature it. Instead of adding 2 to the power, add 1 less than 2 to the power. add the full size thing on n bits. So full of 0 is 0, full of 1 is 1, full of 2 is 3, full of 3 is 7. So in particular, full of 0 is 0, and full of 1 plus n is 1 plus 2 times full of n. And now it's really easy to tell 0 from successor, and it's really easy to tell even from odd. To say vectorized application is silent, but replication of individual things is explicit. We say how many you want. And that will give us not only map for one input, one output functions, but map for row of inputs, row of outputs. And at the moment, you'll see Craig has to implement map the usual way, because we haven't done this yet. But it seems like another way to get paid for bothering to make sure types turn up when we need them. Okay, goodness me, it's the first time in my life I've ever been almost on time. So yeah, I've got plenty of other stuff, but okay, my key messages are that it does make sense to rethink functional programming to prioritize working with monoidal structure and maybe spend slightly more syntax on supporting the kind of higher order Cartesian closed structure. And, even before you switch on kind of clever global constraint-solving machinery, like kind of unification and, SAT solving and Gaussian elimination or whatever you feel like doing, just being a little bit more careful to manage the flow of type information locally gives you a hell of a lot that's just checkably local. And if you're a bit neat, you can make the stuff that you want to be cheap silent just by figuring out where else you need to be explicit to pay for it. So yeah, global constraint solving. I'm not saying we'll never do it. Sooner or later, we'll just get fed up writing those extra lengths and those extra types, and we'll, bolt on some kinds of solvers. But it's really interesting to see how far we can get without flipping the big switch on the wall. Meanwhile, I've been having several other monoidal adventures recently. I'm very interested in types of tensor structures, particularly if they're indexed over other sorts of tensor structures. I remember years ago, somebody asked me, there must be loads of dependent types in spreadsheets. And so you can imagine that, yes, a spreadsheet is made sense of in terms of the data in its row headers and its column headers. The things in the cells tell you something pertinent to about an individual in one row and an individual in one column. So we're interested in kind of higher dimensional rectangular structures indexed over elements of lower dimensional rectangular structures. You can imagine a three-dimensional array being pointed into by kind of spreadsheets on all of its faces. So this is the thing that jacks up through the dimensions. How on earth do you do it? I've been thinking quite hard about that, about kind of brick-shaped data structures indexed over other brick-shaped data structures. And the other thing I've been thinking about is if I ever want to prove anything about these programs that live in the monoidal world, I'm going to want, at the minimum, not to have to pay for the kind of intuitive string diagram deformation intuitions that we have about when two string diagrams are really telling us the same stuff. So if we're actually building that stuff out of commas and semicolons, then we really don't want to have to be shoving those things around to see if they're the same diagram manually. Correspondingly, I'm really interested in building, in finding good normal forms for these things. And it seems like you've got to do some symmetry breaking. So basically it goes, yank a wire and see what you find, right? If you find you've yanked a wire that goes all the way to the output, then great. but you've also split space in two and trapped a bag of scalars. Um, Meanwhile, sometimes when you yank a wire, you find you've actually got a component, and then you need to think, well, okay, who's consuming the outputs of that component, and what other inputs do those things demand? So you end up building things which talk about how you use the inputs you've got and which other inputs you needed to finish that job. So you end up building shapes that look a bit like staircases. So there's definitely some progress happening there. I don't know, I'll finish with an anecdote. I used to sort of teach all day on Friday mornings and then walk into our research lab, Livy Tower 1310, some of you will know it, and I would occasionally walk in and bellow, "Is anyone in this room not working with monoidal categories?" And then I looked around and they just, no is basically the answer. So yes, the monoidal adventures continue thick and fast. And I hope you have fun when you actually see some real BRAT programs coming up in a moment. I'll stop there.
Hi, thanks for the always very amusing talk. I am really interested in this idea of not paying the price for diagram deformation. And it seems to be wrapped up in this issue that you were talking about of never doing arithmetic in your dependent types. So one of the things that the diagrams give you is associativity for free. So I put three things together, and I don't need to remember that I made a list of the first two things and the second and the third thing. I can just immediately plug the second and third thing into the next thing.
Yeah.
But to do that,
We're going to unite these in one language with Bratz. So the way that this normally goes is that we generate our circuits in the classical fragment, and then we go run those, get some data back, do some post-processing, and then we repeat the cycle. If you're doing some sort of variational algorithm ad infinitum. And it's our notion of quantum circuits isn't the strictest. We have classical bits, which are unrestricted. We do the implicit bang that Connor talked about. So if you have a bit in a circuit, it can be copied or discarded. And we can inspect whether they're true or false and decide which gates to do next in the circuit. So we have a little bit of classical control. These days on some machines you can do a fair bit more than this, but we're limiting just to branching on booleans at the moment. And this classical control is always device dependent, so your mileage may vary. I'm going to work through an example of an algorithm from the literature, magic state distillation, in which we prepare a whole bunch of n approximations of the magic state that we want, and we're going to try and make a better one. And we do this by applying or misapplying, not in exactly the way it's intended, some decoder from quantum error correction, which leaves us with a bit saying whether we got the state that we wanted, in which case the wire at the top is the state that we wanted, and we can plug that into the rest of our circuits. Otherwise, we're going to reset the target qubit and then start all over again. And this is interesting as an example of the recently demonstrated repeat until success style of programming, in which you try to do the thing that you want and you check whether you won. Otherwise, you can keep going until you get the answer you wanted. So Bratz syntax, concretely, a little introduction. This is what function types look like for kernels. We have row types, naturally. So this circ function has 2 inputs and 2 outputs. And the top thing is how it's intended to be used. It's called like a normal function. This is just syntactic sugar for saying that circ is a classical thunk, which embeds this commutation. So all of the types in this function type are from the kernel world, and then when we make a thunk, we can copy and discard that to our heart's content, because it's just a recipe for building a circuit, and it doesn't embed any quantum information. When we write the body of the circuit, you can see the same thing going on with the braces. The actual computation we're doing is next to the purple brace, and then we're embedding it into a classical thing. And this is very much like what Connor just showed. We're using the same comma and semicolon to put things next to each other. So you can read this top to bottom, just like a string diagram representation, which is also very similar to the standard circuit representation. So on this side of the comma, we have the H and T happening on one wire, and then on the other one, we're just doing the identity. And we have a bunch of built-in gates, like HST and controlled X. So between 2 worlds, you can have very similar looking programs that are differentiated with the choice of arrow in the function type. On the top, we have a kernel, which is denoted by the lollipop, which is to say that all of the input and output types have to be kernel types, like qubits or bits. And then In the bottom, we have an arrow where we have a richer array of types for classical programming. And it's, the type checking goes a bit differently. We have linear typed qubits in the quantum fragment, so we'll complain about this program because it's discarding one of them, and we'll complain about this program because we're using one qubit twice. So with that, we can go on to build the first part of our example circuit, which is the decoder in the middle, which is just a bit of a gnarlier version of what we saw before. I've written the string diagram next to it for to make things clear, but we're just composing the gates that we want in the right place to say which qubits they're acting on, and doing some swaps to make things resemble the circuit, the string diagram semantics. The red things, the key difference between this example and the last example is that the last example had a row type input and a row type output. And here the row types are unary, but they contain vectors. So the red thing at the top is fan out, which takes a vector of constant length and turns it into a row type of that length. So we're taking our vector of 5 and turning it into the 5 wires at the top of the string diagram over there. And then at the bottom we have fan in, which is the opposite. If we have a constant length, which we do because we've stated it in our type signature 5, then it will take the first 5 wires and pack them up into a vector. So taking the bottom of the diagram and packing it back up into our vec qubit 5. And it's, as in Connor's second adventure, we have some more interesting types going on in the classical world. I've written this identity function, this very simple identity function that's specialized to qubits on the top as a kernel. On the bottom, we can write the polymorphic identity function by taking an argument where star is the kind of classical types. So give me any classical type, and I'll give you an identity function on that type. Luckily, we can use the classical world to make simple kernels using these types. So as Connor showed, we also have a second kind, dollar, which contains kernel types, and we can write the same function here and it'd replace the specialized qubit that we had over here with something more interesting based on the type information that we had in the classical world when we were constructing this kernel in the first place. And it's something to note is that star and dollar are two sets of types. They have no overlap. We have a quantum bit and it's a classical bit, and any lifting you want to do from a quantum bit to a classical bit has to be explicitly by running a kernel. So with this in mind, using interesting type parameters to generate simple kernels, we can write some well-established functional programs like map, which is a bit of a crutch, as Connor mentioned. But we take, as the first two arguments, the input type and the output type, some function from input to output, and it's the length of a vector that we want to lift this to. And then we're going to produce a kernel which does this transformation on every element. And a key thing to note is that our pattern matching is happening in the Brat world. So on the right-hand side of the equals, in the braces, we have our kernels. But the important pattern matching is here and here, where if it's 0, we know that the input and output of our kernel is going to be a vector of length 0. So it's easy to match on the empty vector, and we know what to return. In the other case, if the length is a successor, we know that cons must be a valid constructor of our vector in the kernel, so we can take it apart and recursively call map with the predecessor. And it's important to note that because of the type information that we've acquired by matching on our arguments, these patterns in the kernels are irrefutable, thus avoiding costly errors while you're running your circuits because you didn't write all of the possible matches for your pattern. And with this in mind, we can make the decoder from before a little bit nicer just by moving the fan in up and adding a map over vectors instead of a bunch of H gates on the row. Another classical program we might want to use, or another well-established program that we're going to want to use for measuring the syndrome at the end. The syndrome is constructed by mapping OR over all of the, or folding with OR over all the results of measuring our auxiliary qubits. So we're going to use this in a second, and something notable is how weird the function arguments are here. There's x to x, and it's produce an x. This says that we can, we have to be using copyable and discardable things as the argument to this, which can be bits, or vector of bits, or some vector of rows of bits. And then we can write our any function easily with OR, which is I've written elsewhere, and the thunk, which takes an empty row argument and produces false. So now to go back to the rough thing, this measure syndrome, we're separating out our target qubits from all the auxiliary ones, measuring them all, and if any of the measurements turned out 1, that's our criteria for rejecting versus rejecting and starting over again versus continuing. So that's this measure syndrome function. We're just going to measure all, which is very much like mapping measure over a vector of qubits. And then our result is going to be a vector of bits and a vector of leftover money, which I'll talk about in a second. And that we're going to do the any that we just defined on the bits and the identity on the money. When you measure a qubit, we're assuming that we're programming for the paradigm wherein you can destructively measure qubits and then reset them in place. So we have these two functions. If you have some money, you can cash it in and get a fresh qubit. And if you measure a qubit, then you get the money back to instantiate a qubit in its place, and you get the result of the measurement. This way, the sum of qubits and money in the circuit is constant, so you can't exceed your qubit budget. And everything is a value, which is very pure and functional in contrast with some other approaches like not caring or having some monad which tracks all of the freshes and measures, or inferring some type parameter. This also lets us do things like pack money into structure and then map over it if we want to. Okay, and now with that in mind, the first part of our circuit is taking a bunch of money and it's creating a rough approximation of the state that we want. To do this, we use the fresh function that we just saw and then do a couple of rotations. And it's, as has been said, we're using our invisibility budget to splice things into place. In our white box here is the kernel we're building, and its magenta boxes are kernel functions. And we're producing these using the yellow boxes, which represent classical functions. So phi, for example, is a classical value created by running this arc cos. And the type signature of our rotation gates are that they take a float parameter and then they return a kernel from qubit to qubits. And then we take that kernel and when we call it, we splice it into place with this blue wire by evaluating it in the kernel context. And we can now just use map to take this, prepare one noisy qubit to however many we want. Yeah, the last step in our algorithm is looking at the bool and deciding what to do next. So we're taking some row in this function I've called redistill if bad. We have our target qubit, our syndrome, and it's a bunch of leftover money from measuring all the auxiliary qubits. And it's then in the false case, we just give back the qubit. Otherwise, we're calling distill again and starting over. Distill is the outer function that does this whole thing. I've showed that we can generalize prepare noisy to n qubits and measure syndrome to n qubits, where n is a type level natural number parameter. The choice of decoder is more forced, though. We can't generalize this. We have to take some off-the-shelf error-correcting codes. In this case, we've selected a 5-qubit one. So that part of the algorithm isn't generic. But we can put it all together now. We start off with a vector of money of the right size, and we're returning the target qubit and the leftover money. So we're going to prepare a bunch of noisy states, run the decoder. Uncons is just popping the head off of this thing because we know the length is 5, which is a successor. Measuring the syndrome and the auxiliary qubits, and then potentially starting over if bad. And the way that these types are written, everything just plugs into each other. So we're writing all of these as compositions where the result of prepare noisy feeds into decoder, feeds into uncons, and so on. All right. So that's our example. There's a couple of things we didn't talk about for time. We have nicer ways of permuting rows of qubits, rows of types, because they're all named, but I didn't go into that. You don't strictly have to do explicit swaps on everything. Our type checker makes it easy to write things like an operator which takes the remainder of the row and just passes it through unchanged. We have, for our vector lengths, the language of expressions in one variable that Connor talked about. And another way to get your money back for strong typing discipline is with some interactive programming. So we have typed holes and a little bit of trying to guess what could go in the hole. And this is embedded in an LSP mode, which is quite early days. And it's what we're planning to do next. Connor's alluded to a lot of it. Vectorization, so that we don't have to do our map on one thing to one thing. We can instead take arbitrary row functions and lift them to vectors. And we'd like to apply thinnings to make even nicer ways of addressing qubits within a row than pooling them by name. Type inference could let us drop a lot of these type parameters, which could be easily inferred when we're calling map, for example, and given the types. And the biggest thing is code generation. Brat at the moment is mainly a type checker. We create some internal graph representation of the program, but we're not yet able to run it in anger. And it's, at the point that we can, then we're going to release it so that other people can play with it. But for now, it's just being developed in private. So that's about the shape of it.
Thanks for this presentation. One question about code generation.
Mm-hmm.
What kind of code would you generate? I mean, what platform, what intermediate language, anything?
That's an excellent question. We are specifically planning on targeting an intermediate representation that we're developing at Quantinuum, along with some of the people here. Mark Koch will talk about this later in his Guppy talk. But we've been involved in the development of this IR, and it's going to be a pretty natural fit when we get around to writing the code generation.
Excellent.
Hi. It wasn't clear to me, I guess, the advantages to the money system as opposed to what I guess I would find more intuitive, which is just when we measure a qubit to just reinitialize it. I was wondering if you could touch on, I might have just missed it, some of the advantages of using this money system.
Well, to reinitialize the qubit, that's kind of like just automatically calling fresh after you measure. I wasn't looking at a system like that to compare at the time, but it seems pretty similar to our approach. The only difference being that semantically, you know that money is going to be cashed in the zero state, and you don't necessarily know when you're looking at random qubits whether they were made by coming out of a measure and can be assumed to be in zero state.
Okay.
Speaking of money, since we're about it, how do you track which qubits are released? You see what I mean?
Yeah, in BRAT, all of the money is identical. We don't particularly care about which one's which and consider that to be a lower level compilation task.
Makes sense.
I know you mentioned a little bit about variable binding for getting rid of the explicit swaps. Also, a really convenient way to write these little circuit fragments is using this kind of chasm-style indexing, right? I say I want a CZ going from my first qubit to my 9th qubit, not first qubit, swap, 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 9, swap, swap, swap.
Mm-hmm.
Is there some kind of feature, or can that be easily sugared into the language?
It's in our plans, certainly, but at the moment there is not a super easy way to do this. I don't have the slides up. But when I say we want to use thinnings to apply computations, I want to be able to say things like, I have an operation that acts on 2 qubits and returns 2 qubits. I have some vector of qubits. I want to apply this specifically to 0 and 9, for example, and then we're going to narrow the row of qubits to just the 2 that we want, and then thin it back out. So I think this will end up looking fairly close to working with vectors, but then slightly strange.
Okay.
Which I think will be for the better, personally. Strange, not in the pejorative sense.
Okay, thanks everyone, and thank you, Craig.
Have you got an adapter? An HDMI? There's one here.
So Up next, we'll have Andrea Coledon talking to us about circuit width estimation via effect typing and linear dependency.
All right. Hello. Today I'm presenting joint work with Ugo Del Lago about the resource estimation of quantum circuit description languages. So just a little bit of refresher. What is a quantum circuit description language, or QCDL? It's basically a paradigm of quantum programming in which programs are actually classical. They execute on traditional machines, and they produce a description of a quantum computation as a result, usually in the form of a circuit. So we have quantum primitives, quantum operations, but instead of carrying them out, we basically buffer them to some internal representation and return that representation in the form of a circuit, and alongside the result of the computation. And so then we can take those circuits and combine them or manipulate them and describe more complex circuits, or we can just send them to quantum hardware for direct execution. And this is a paradigm that's been adopted by many mainstream quantum programming languages in the past decade, such as, for example, Qiskit or Quipa, which is a quantum circuit description language embedded in Haskell. So, for example, in Quipa, I can write the following function, which does some quantum operations, and then when I apply it to an adequate argument, I get the circuit as a result, together with two references to the output qubits bits of this circuit. And the good news about this is that because these languages are essentially classical languages, we can leverage the expressive power of modern, general purpose languages such as Python, Haskell, you name it, to do some very complex circuit construction and build very complex, describe very complex quantum algorithms that translated to circuits mean millions of qubits and trillions of operations applied to them. And the bad news is that real-world quantum computers at the moment are nowhere near this scale. They're very small and unreliable, and this means that it's very, very easy to write programs in QCDLs which vastly outperform quantum architectures, even on very modest input sizes. And so, for this reason, in this scenario, we thought that verifying the resource consumption of programs written in these QCDLs was a very worthwhile pursuit. And specifically, we wanted to tackle the number of qubits required by a computation. So in this context, the width of the circuits produced by a program in a QCDL. And in this sense, our contribution has been a paradigmatic quantum circuit description language in the tradition of the Proto-Kuiper language family, endowed with a refinement type and effect system that allows us to derive concrete upper bounds on the width of the circuits produced by a program. And these bounds are parametric, and we'll see in the size of the input of the program, and we'll see in a second why this is relevant. And together with the usual proof of correctness that tells us that our analysis is in fact sound with respect to the circuit building semantics of the language. Okay, so let's have a look at this language. This language is our language, which we call Proto-Kuiper R, is very strongly inspired by Proto-Kuiper M. At its very core, this is a effectful lambda calculus. So we have a distinction between terms and values. Return turns a value into a trivial computation, let sequences computations, and so on. And the side effect of this lambda calculus is precisely that of building a circuit. So circuit construction happens in a way behind the scenes as a side effect of a computation. And we have, of course, bespoke data types and constructs to perform this circuit manipulation. So to start, what we see written as L is a reference to a free wire in the underlying quantum circuit, which we call a label. what you see highlighted now is a boxed circuit. So I just finished saying that circuit construction happens as a side effect, but we can also have a way of turning the circuits that we build as a side effect into data for reuse later on, and for composing simpler circuits into more complex computations. And this is also the kind of term that encodes primitive operations in the language. So we assume to have one such term for every primitive operation that we want to carry out. And the basic, the most fundamental construct of the language is the apply construct. Basically, apply VW appends a boxed circuit V representing some general quantum operation to the wires identified by W in the underlying circuit. So as a little bit of an example of how circuit building, oh yeah, and we also have like a limited form of recursion via hard-coded fault operator. Okay, so to have an idea of how circuit building happens and what kind of considerations we have to take into account when we analyze width, let's consider the following program. It takes as input a qubit. It applies the initialize operation init1 to the circuit, meaning that it basically emits an initialize operation to the circuit. Then it applies an operation to the two qubits that we have, and then discards the auxiliary qubit that was just initialized. And so when we run this, we get something like this, where the circuit is precisely encodes the operations that we carried out in the function. And it's very easy to see that the circuit has width 2, because we have one input qubit, and then we initialize an additional qubit, and then it's very easy to conclude that the overall width is 2. But then we might want to take this function and apply it twice to the same input, getting a circuit that looks like this. And in this case, we have one input qubit and 2 initializations, but still the width is 2, because we perform some, we discard the auxiliary qubit before we initialize the new one, and so we can do some form of recycling. So first of all, we want our analysis to be able to capture reuse of discarded wires. But then these examples are nice, but they're not really what we would call a quantum algorithm, because usually when we talk about quantum algorithms, we mean circuit families that are indexed on the size of the input. We can write this in the language. For example, Hadamard n is a function from list of qubits to list of qubit to list of qubit. And basically what it produces is the following circuit that just applies the Hadamard gate to all of its inputs. And this is like a pre-processing stage in many quantum algorithms, as you will know. And it's very easy to see that there is no way to give a fixed width upper bound to this circuit, because the width of this circuit is n, where n is the size of the list in input. So not only we want to be able to track reuse, we also want to be able to track this form of dependency, which means that our bounds ought to be parametric, because otherwise we wouldn't be able to capture. We would only be able to to analyze single circuits, and that's fairly uninteresting. Okay, so let's see how we can use types to actually do this kind of analysis. We start from the basic, almost universal proto-Kuiper types, which form a linear nonlinear type system in which qubits and bits and functions have linear types. Circ is the type of circuits seen as data. And we extend this kind of type system, which does nothing in terms of resource analysis, in 2 directions. One direction is that of refining types in the style of the Lago and Gabardi. And what we do basically is take key types and annotate them with indices, which are just arithmetic expressions on natural numbers and variables. So if you look at the grammar, this is a natural number, this is a index variable, which tell us some interesting information about the elements of this type. So for example, circ ITU is the type of boxed circuits of width at most I, with input T and output U. List I of A contains lists of exactly I elements. And the most convoluted annotation maybe is that of functions. functions are annotated with two indices. The first one tells us what the upper bound to the width of the circuit that the function produces once we apply it to an input of type A. And the second one tells us exactly how many wires the corresponding closure contains from the outside environment. So that's a bit oddly worded, but basically how many wires the function captures from the environment. And we'll see in a second why this is relevant. And the second ingredient in our analysis is effect typing. So our type system revolves around a typing judgment of this form, which reads for all index variables in theta, under typing context gamma, which gives types to variables, and label context q, which gives types to the wires in the underlying circuit. M is given type A and builds a circuit of width at most I. So in this case, I is still an index, but it's an effect annotation that tells us something about the side effect released by the program. We have a similar judgment for values, which however are effectless. And here the universal quantification over the index variables in theta allows us to regain some form of dependency. Because if we write something like this, we can basically express that the function Hallerman n that we saw earlier as type for all I from list I of qubit to list I of qubit, building a circuit of width at most I. Okay, so let's see some interesting rules of the system. Apply is the most basic rule. From the typing perspective, that's pretty straightforward. If we apply V of input type T and output type U to a value W of type T, we get a result of type U. From the circuit building perspective, what's happening here? So V is a box circuit, which means that there is an associated, a circuit object associated to it. Let's call it CV. And apply does nothing but basically turn that datum into a side effect. So the circuit that gets built is this one, and the inputs to this circuit are the wires that are contained in contexts gamma 2 and Q2, because these are the contexts under which we type W. And in this case, it's really easy to conclude what the overall width is, because we know by this annotation that V is a circuit of width at most I, so we conclude that apply VW builds a term of width at most, builds a circuit of width at most I. Let's make things slightly more complicated, although it might not look like that. What is the effect notation of return V? So at first glance, okay, return V is a trivial computation, so we might conclude that it does nothing. So basically, it builds the empty circuit, and it has width annotation 0. But that's not the case, because wire references in this language are values, and so V might contain many references to the wires in the underlying circuit. And so morally speaking, the circuit that's being built by return V is not the empty circuit, but rather the identity circuit on the wires contained in gamma and Q, under which V is typed. What is the width of the circuit? Well, the only way that we have to conclude something about the width of the circuit is to find out how many wires are contained in gamma and Q. And we denote this quantity with the hash symbol, which will read the wire count of gamma or Q or gamma and Q as a shorthand. And this is a central element of our type system. We obtain this quantity in a very easy way. In fact, we just traverse the typing context, look at the types that are mentioned in it, and derive from those types an estimate of how many wires are represented by that type. And that's fairly easy for most type, except for function types, because from a function type we cannot say anything about how many wires are inside the corresponding closure. So we have to keep track of this value explicitly in the second index J, which is precisely the wire count of this type. And this annotation is generated in the abstraction rule in a very similar way as it is generated in the return rule. All right, so one last example, the let rule. Type-wise, this is fairly standard. From the circuit building perspective, what is going on? Basically, M builds its own circuit, which we call Cm, and which by the premise we know is the width of Cm is bounded by I. Then this circuit has some outputs. Because of linearity, all those outputs must be bound to x of type A. And still, due to linearity, all these outputs containing x of type A must be taken as input by the circuit built by the second term n, which by premise has width at most j. So at this point, it might be natural to conclude, okay, we have like one thing of width I, one thing of width j. We are putting them together like in sequence. The overall width must be something like the maximum of I and j, right? There's a catch to that, because x of type A is not the only input to Cn. N is also typed under gamma 2 and Q2, which contain wires, which must pass alongside Cm while we're building, morally speaking, must pass alongside Cm while it's getting built. And these wires have a width that adds up to the overall width of the left-hand side of the let. So the width of this left-hand side is actually I plus the wire count of gamma 2 and Q2. And the overall width of the let expression is the maximum of I plus the wire count of gamma 2, Q2, and j. And this is the last rule I'm showing you. I'll spare you the rule for fold, because no one deserves that on a Saturday morning. Let's talk well-typedness. Like in most other ProtoQuiper instances, it makes no sense to speak of the well-typedness of a program in isolation, because a program manipulates a circuit, and thus it must be paired with a circuit that provides the right kind of wires. So, well-typedness we write as such, and we read that configuration Cm, where C is a circuit, M is a term, is well-typed with input Q, output L, type A, and effect notation I, that is with at most I, when C has the right signature and provides as outputs, as some of its outputs, the wires that are used to give type to M. So it's something that's illustrated in the figure. And okay, so what can we say about well-typed configurations? We model circuit building semantics through a big step evaluation relation that tells us that M evaluates to V, and in doing so, as a side effect, updates circuit C to circuit D. And what we can say about well-typed configurations is, well, subject reduction, that tells us that well-typed configurations stay well-typed when we evaluate them, but also, and most importantly, total correctness, which tells us that if a configuration is well-typed, then it evaluates to something, and in particular, M evaluates to V, and in doing so, as a side effect, it extends C with a subcircuit D, which has width at most I. So this tells us basically that the circuit that the term extends the underlying circuit with is bounded effectively by the effect notation that we derive through our type system. All right, so that's pretty much it. As further work, we are working on the implementation of the type checking procedure for this language, and we're also in parallel working on the notational semantics for the language, which is something that most ProtoQuiper incarnations have that we still do not have. And other than that, we would like to generalize this analysis to other kinds of resources, such as the gate count of the circuit, so its size, or the circuit depth of the circuit, or whatever. So that's pretty much it. Thank you for your attention.
Any questions?
Thanks for the talk. I can kind of see how you could generalize this to gate count. Still a very syntax-directed thing. I just need a track. You know, when I put a gate, I increment something. Do you have some ideas about how you would do this for depth?
Yes, and it's very different actually, because we found that the only way to have a good estimate on depth was to keep the analysis at a very local level. So our idea is to basically take where are they? Well, basically the qubit and bit types and annotate them with indices that tell us basically, okay, this is a label, this is a wire reference of type qubit, and also the sub-circuit that's rooted in this label has a certain depth. And then try and compose this kind of local annotations, and in the end, only in the end conclude something global about the circuit. But still, this is still in the very early stages of exploration.
Thanks.
So the newest versions of ProtoQuipper, have both dependent and linear types in them, and it seems like the dependent types do a fairly good job of capturing the width of the circuit. So I was wondering, if you could talk a little bit about the difference, and B, whether or not you can integrate this with the newest ProtoQuipper.
Well, our original goal was to try and see if with ProtoQuipper D we could do something similar, and in principle it looks like yes, it can be done. However, at some point we wondered whether it was possible to have some much more lightweight verification of this property, because it seemed that we were doing the same thing over and over again. Our idea is that because these are basically refinement types, we might be able to automatize a lot of the basically proof work that goes into proving that things match up correctly. So this was our main motivation for going in this direction. I don't know how we would go about integrating ProtoQuipper D and this kind of more refinement type-oriented analysis.
Because specifically you don't want to deal with the complexity of ProtoQuipper
Yes.
D. I see. Thank you.
Nice talks, thanks.
Thank you.
So, how tight are those estimates?
Well, we have no real formal result on how tight they are, but they seem quite tight. We haven't done much experimenting with very big quantum algorithms, but for example, we did manage to type check the quantum Fourier transform family of circuits, and in that case, the upper bound is exact. But then again, that's expectable because you don't have much recycling going on. On very simple examples, it is exact. We still have to find a counterexample to that, but we do believe that they exist.
So you have an implementation?
Yes.
Okay.
A very
prototype.
contrived
A prototype.
implementation
Yeah, yeah.
of a QFT, but yes.
Okay, thank you.
So my question was about recycling.
Mm-hmm.
I don't think you've shown any inference rule that showed recycling, or if you did, I didn't.
It's in a way, it's implicit in the let rule, in the fact that we compose with a maximum.
Okay, fair enough.
That's implicitly assuming that we can reuse any wires that do not appear in basically in the output signature of the first circuit. We can reuse in the second.
Makes sense. And I'm going to ask you the same question I asked about Bart. How would you keep track of which wires can be recycled?
That's a nice question. You mean basically having some actual constraints on when a wire can be recycled and when it cannot be recycled,
Yes.
right?
I mean, it doesn't have to be in a type system.
We okay. So basically, what happens is I don't think I know how to explain this very briefly because it's kind of an emergent property of the whole thing. But basically, what happens is when we discard something, and I maybe can find an example. No, it was here. When we discard something that has a width, but it doesn't have an output, because the discard operation basically outputs the unit value. And this together with the let rule that allows us to compose computations in sequence through the combining effects with the maximum operation. Basically, that implicitly allows us to treat that wire as a discarded wire, as opposed to a wire that must be kept alive in a way. Also, linearity plays a big role in this, because we cannot just forget about linear wires. We're obligated to do something with them, even though it's an op. We have to take them into account.
Thanks. Thanks very much.
Thank you.
We ran quite late, but we'll try to start the next session at 11 as the schedule says. If you're speaking in that session, come see me. compilation. And the first speaker is Julian Jelishev from Oxford. No, from Bristol. Sorry.
Both.
Okay. I don't know why my slides are. Oh, they disappeared somewhere. Oh, I can't find them. Okay. It's going to take a while. Are they here? Okay. Okay. Hi everyone, I'm Julian and I'm going to talk to you about recursive string diagrams. It's not really compilation, there's some compilation, but whatever. Okay, so let's start. So why did we do this? So this is joint work with my supervisor Alex, who's going to speak after this. So there's this thing called the ZX calculus. I don't know who's just heard of it. Yeah? Okay. Also, I was going to ask, do you like category theory? Raise your hand. Okay. Okay. This is just for... So, okay, doesn't matter. So this is a graphical language for quantum computation. The only thing I'm going to point out about this is the wires here are single qubits, okay? That's all you need to know. Next thing, so there's an extension called the scalable ZX calculus, because like diagrams in ZX tend to kind of become very, very large and they're unwieldy. So in here, the bold wires are registers, so you have a register of qubits. And the thing I want to point out is this thing here called dividers and gatherers. So you can peel wires out of a register, so it's fan in, fan out, and fan in basically, and you can gather them back up. Okay, so we started thinking about the scalable ZX calculus, and we wanted to do kind of a QFT in scalable ZX because they have this looping construct, but then it was a bit difficult, and then we said, what about recursion? Okay, so that's where this is going. So, okay, recursive diagrams. I'm going to give an example of what I'm going to talk about, and then I'm going to explain how we basically did this. Okay, so let's focus on the thing on the left here, okay? Forget about this here for a moment. This is a box called R, and it's a family of boxes because it's indexed by a natural number. Okay, so let's look inside now. So the thing to note is we have this thing here, Rn-1. So we're basically recursively using this box inside. And this is, the dividers and the gatherers I draw with this kind of black line. So this is kind of a thing we want to recursively apply on our register. And we're basically just saying, okay, we have this thing, now let's take a wire out and then do the same on n-1. So if we kind of plug in n for 4, for example, we get this thing over there. Yeah, makes sense? Okay, so so these dividers and gatherers in this case are really just syntactic sugar. So you can kind of unfold them out, and this is what you'll get. Okay? And this is all really I want to talk about is what are the semantics of these kind of diagrams, and why would we want these, okay? So I'm going to give a more involved example, basically, to kind of try and prove why is this useful. So I'm going to show you the quantum Fourier transform, okay? And this is it. This is a family of Fourier transforms for any number of n here. So the thing I want to point out here is all the bits in blue and red, they're both just for the recursion, right? So you can build these patterns of recursion that kind of build different kinds of circuits depending on where on the register you go. And the bits in black are just what's needed for the Fourier transform. So rotation in Z and a Hadamard gate. And you have this n that you can use around, so you can use the n in the in kind of here in the parameters for the RZ. So it kind of makes it pretty clear what's happening. But this kind of looks a bit weird, and the semantics for these diagrams are things called paramorphisms, which is a kind of a recursion scheme. So you might wonder, why go this roundabout way to make this thing happen? And we do this because the paramorphism comes with certain laws. So you have kind of equations, and you can do equational reasoning between these kinds of recursive diagrams. So I'm going to give you an example. So, this is basically the circuit of the Fourier transform. So we have an embedded domain-specific language in Haskell. So if you build this thing in Haskell, so you can translate the diagram kind of very easily into code, and then you run it, and this generates this circuit, and then this is Kazan basically. You can compile it down to Kazan. Okay, so let's show why is this useful. So I take this QFT and I mirror it, and I can get the inverse basically. So if I get the inverse in the gates in there, and using these laws that I'm not really going to tell you what they are, but I'm just going to show you some examples, I can simplify this further, okay? So first of all, I can kind of drop the blue recursion out, and I end up with this thing. So there's another thing where I can actually drop all of these things, I can cancel out the left and the right. I'm left with this, all Hadamard, and I get the identity. Okay, so we can do these equational reasoning, even automatically in the code, in the Haskell, or you can do it like as pen and paper. And you can see that this kind of like makes a diagram, otherwise it'd be very big and willed into kind of something small that you can play around with. And this thing applies to kind of any language based on a symmetric monoidal category. So you can, I've used circuits as an example, you can apply this to ZX or something else. Okay, so how does it work? So we have this, okay. So you give it a monoidal signature, and for our case, we kind of define a type of diagrams, which is just the free symmetric monoidal category. You can drop the symmetry, but you'll need to change some things if you want to down the line. So, or basically, we have a type of diagrams which is just this. So you have a compose, sequential compose, you have a tensor, and these are your types, so the wires and the boxes. We have an empty diagram, and also we have this bottom, because we're kind of lazy, so we're basically kind of a runtime scenario. If you're trying to compose something and it doesn't work, it gives you bottom and say, okay, we're done. Okay, so have people seen this diagram before? No? Okay, so this is a diagram with a hole punched out, basically. We call them combs because you can have as many holes as you want and they kind of look like combs. So I'm going to be using these things. So these things are also kind of the shapes of something called a coend, but I'm not going to even go into that one. But they're also equivalent to a monoidal lens or an optic, if somebody's heard about this. So we basically, and these things form a category, they're morphisms in a certain category, this category optic C. So you basically get a category C, the objects of this optic C are pairs from C, and then the morphisms are going to be these combs. So basically, this is why this notation is here, because you have, this is a morphism from this side to that side, basically. That's why you think of them as functions between diagrams, is because I can plug in a box here, and then this kind of fills up, and I get another box. If that makes sense. Okay. So, yeah, they form a category. This is how we compose them. You can imagine, so the combs, you can build them with these L1 and R1, but like you can just imagine a comb drawn over these things. So you basically stack them like that. Okay? If that makes sense. Okay. I'm going a bit fast. I'm going to slow down at some point, I promise. We can also do the same. So the way I built a type, a set for all the diagrams, I kind of got this category, got all these morphisms and bunched it in a big bag and said, that's my diagram type, basically. That's all the diagrams that I could have. We're going to do the same for combs. We're basically just a big disjoint union for everything, get them all in a bag. We also tag in bottom and that because we're working in this kind of runtime setting. Okay. So we have these combs, and I said we can look at them as functions between diagrams, and it's kind of pretty easy. It's basically we define this plug, which takes in a comb and a diagram. I'll kind of reverse this here, but like you plug the diagram inside the comb. If it composes, you're fine. You get back your box. If it doesn't, you say bottom, and that's it. Yeah, makes sense. Okay. So, and yeah, you can basically use this kind of. I use this notation like C bar to mean kind of the function between diagrams that you can get from a comb. Okay. Okay, that's one bit over. So now the recursion part. How are we doing recursion is something called recursion schemes. So these are types of recursion. So is anybody familiar with a catamorphism? So if you're not, if you know what a fold is, that's what a catamorphism is. It's just a fold, okay? So you're basically given a non-recursive function here. So this f is an endofunctor, okay? Or you can think of as a data structure. And then this thing tells you how to evaluate one layer of your data structure. So it's not non-recursive thing. And from this, you can obtain a recursive function, which is this thing, banana psi here, which tells you how to now consume recursively your whole data structure down to a carrier type, this thing here. I'm going to give an example. So if I replace f with 1 plus x, its fix is natural numbers, okay? And then I say a carrier type is a string. this is kind of the commutative diagram. So I need to give this thing to convert a natural number to a string. So it just tells me how to peel on one layer of that natural number. If you think of like successive, like, yeah, and then I can consume everything. So as an example, if you can kind of unfold this co-product here, and these are kind of the two things you need to give. You need to give your base case and your kind of step case where you can consume that things. So here's how it works. So I have a natural number. So the phi 0 is just going to give me my nothing case. Base case gives me 0, and then this is just a function from string to string, my pi star, that kind of wraps around the base case. Then in Haskell it's just this, right? So the phi 0 just gives me nothing, and then this is my pi star here, which is just from string to string. Okay, so it's not really that complicated, although when you think about the categorical semantics, it gets kind of a bit. Oh, yeah, sorry. Okay. So, okay, for our purpose, we need a kind of a different flavor of this called the paramorphism. So with the catamorphism, you kind of don't have access to the things that were used to produce your accumulated value, right? You can think of this thing consuming down the data structure, but at every step, your function just sees what was kind of passed down before. And with the paramorphism, you do have access to this kind of thing. So we're going to use this, basically. And now I'm just going to do the same thing. In our case, we're still using this 1 plus x functor and the natural numbers. Now, however, we're using the diagrams as a carrier type, okay? So what's happening here is I can get, so I need to obtain this function, okay, this function over here, okay, which given a natural number will give me a diagram. So this basically defines a family of diagrams, okay? But to do this, I need to provide the thing on the left, okay, which is 1 plus d times n, so psi basically. So again, I can do the same thing. I split it into two. So all that means is I need to provide this phi 0 and psi star, okay? And these are the signatures. So one is just a diagram, my base case, and the other thing is my step case, but in this case, there's an n there. And if you look at the signature there, it's basically an index comb, right? Remember those combs I showed you are functions between diagrams. And an indexed one is just the functions from the naturals to that kind of thing. So given a comb, I can basically make this phi to make my paramorphism, okay? So that's what we do exactly, is kind of the semantics of this thing is you have this, your diagram over here. This is my comb. So this thing has everything I need, kind of all the work I want to perform recursively. If you imagine my first example where I just have an f that I just applied like this, that's all in there. And the whole is just for the recursion, right? So this is just to show, like this is a stand-in for any kind of diagram that you want to build. And you can nest them, as you saw in the QFT, I had like two things nested together. Okay? And usually we take, if you don't provide a base case, it's assumed to be the empty diagram. But then if you do, that's just the paramorphism of kind of your base case and this comb as a function between diagrams. What I want to point out is this box here then, this box is a family of diagrams, right? So you give it a natural number, it gives you a diagram, and that thing is this kind of paramorphism. So that's how you get recursion, and as I pointed out, it's useful because we have these kind of laws that we can play around with the paramorphism, so you can do equational reasoning, and it's much easier to do this and kind of try to do some proofs and like inductive reasoning with this thing rather than we kind of unbounded recursion. So that was kind of the whole point of this. And it's kind of very easy to implement. That's the other thing is, so in our domain-specific language, what we have is the diagrams are basically a big algebraic data type, okay? So you're building your diagrams. So just as you see them, the QFT there is kind of, I'm going to show you because I think I'm going to have time because I sped through this, which probably is not good. Okay. Okay, so here's how it works, the paramorphism and the building of this kind of recursive structure. So in here, we have our natural number, 3 in this case. So first thing happens, so the other thing I'm going to point out is, when you look at this thing here, it's recursive. You can see like phi 3, phi 2, phi 1. But the way it's built is kind of from the bottom up. So you kind of start here. You get your base case, which might be the empty diagram, might be an identity, might be something else. And then the phi star will take this, wrap 1 phi 1, and then wrap this on phi 2, and this is kind of the index you're keeping. That's why you're using the paramorphism and not a fold, for example, because you are kind of keeping this index around. And the fold is on this type here, right? This is the recursive structure that you're using to build this thing. Okay. So another thing is, if you don't really care about this paramorphism at all, and you don't want to implement this, there's also alternative semantics where it's basically just a composition of coends, and that's all I'm going to say about this. So yeah, so I showed you these recursive diagrams that you can build. So you can implement this very easily in a language. You also have, with the paramorphism semantics, you also have these kind of coend things that you can do if you want to do category theory. And this is applicable to any graphical language you have on a symmetric monoidal category. And there's an implementation in Haskell. So where this is going is we want to basically try more case studies with this, implement more algorithms rather than just the QFT. You can try Grover's and things like that, and see if this kind of equational reasoning helps you to reason better about these algorithms. Also, you can come up with more kind of useful equations on top of those laws that the paramorphism kind of already has. And then we're going to add this in CHIP, which is kind of a theorem prover for string diagrams that Alex, my supervisor, is kind of working on. So you can kind of do inductive proofs. This is the end, but so this is basically just to show you just the code, if I had time, this is the code that does the QFT. So these are kind of the patterns, but this is just a diagram. The arrows are just sequential composition, and the ampersand is a tensor product. And you have these diagrams, and you kind of just compose them together and wrap them in this kind of recursive structure. So that's it. Thank you.
Okay, thanks, Julian. That's very quick, so we have plenty of time for questions. Start with Mark.
So in all the examples you showed, you have like one recursive call to n-1.
Yep.
But you could also imagine things where you want to call n-1, n-2 all in the same diagram, something like this. Would you use histomorphism or something like this to express this? Would this be possible?
Yes.
Fibonacci, for example.
Yeah, you could try more complicated recursion schemes, but I don't really think they're necessary in this case, because you can kind of, if you want to use different structures, you can kind of wrap dn in some other function that kind of gives you kind of different patterns, if that makes sense. But it's definitely, I've wondered about kind of hylomorphisms you can do. There's similar work by Mario Roman that does coalgebra, so deals with kind of building things co-recursively, not recursively, where you kind of build streams. So you could kind of think about building something like this and then consuming it down with something like this. But yeah, that's also could be possible with a kind of histomorphism.
Any more questions? Maybe this is too much trouble to do without a board, but could you show an example where the input object and the output object are different? Like a tree.
Yes, you could. One thing you can do is you can kind of forget about, so you could, it depends how you kind of build this kind of recursive structure, that's all. So I can remove all of this, put this box down here, for example, and then that will give me a tensor of these f's, for example. I can kind of build just across any register. So a tree, that's, yeah, I don't see, so you don't really have to have this output n here, right? You can remove this and kind of still get a recursive thing that just consumes something down, right? So if you imagine this n, if this f of n didn't have any outputs, if just to have inputs, for example, or something like this, you can still use kind of the recursive call, if that makes sense. But you can just pad things around with kind of empty diagrams or something like this. But yeah.
Any more questions? Okay, well, thank you very much.
Thank you.
All right, thanks.
Let's ask Kissinger, who actually is from Oxford.
Actually, I am from Oxford. Yeah, Julian is at kind of both, because he's at the Bristol CDT. He's visiting Oxford to do his PhD. Yeah, so I'm going to talk about some joint work, emphasis on the joint aspect of this. But I'm the one that you get for this, so for better or worse. But I'm going to talk about optimal compilation for parameterized quantum circuits. This joint work with Thomas Lakonen, Richie Jung, and John van de Wetering. Okay, so quantum circuits, as everyone is very familiar with, is a kind of an assembly language of quantum computing. And something that we often want to do with quantum circuits is optimize them. So do the same circuit, but with fewer gates. And the kind of old-fashioned way, I put this up as kind of a straw man because I don't know if anybody ever really did this, but the old-fashioned way of optimizing quantum circuits is to think about kinds of gate identities that we know and just apply them locally to try to get gates to cancel out, right? So for instance, you might know that if I push a couple of Hadamard gates through a C0 gate, it flips around, right? So that's probably a rule that looks pretty familiar. And then a pair of C0 gates could cancel out. We get something a bit simpler. Right? Well, you know, you can do this. A problem with this, though, is you start to think, well, what are my useful gate identities? And you come up with a few, and then a few more, and then a few more, a few more, and a few more. And you kind of wonder, you know, when will this end? Right? I could actually put a line of like 20 slides of just pages and pages of this stuff. And it's part of the problem is that circuits are so rigid, right? So I need to come up with lots of different variations of essentially the same rule. But something that you can do that's a bit smarter than this is I can cut my gates open and get a much more flexible, essentially a graph-type structure. And this thing's called a ZX diagram. So many people have probably seen this before. ZX diagrams are made of these small basic linear maps called spiders. This is always just a rank 2 matrix. It's got a 1 in the top left and an e to the I alpha in the bottom right. So you can think it's like a generalized phase gate. And it's enough to have 2 of these. So I have one with respect to the z basis. I have one with respect to the x basis, whence the name, and they're related by a Hadamard gate. And now this thing, unlike a circuit, is a flexible object, meaning that if I deform this any way that I like, the linear operator it describes is always the same. Okay? And a useful thing about these objects is they satisfy a sequence of rules called the ZX calculus. And actually, you can come up with very small, complete sets of rules for these diagrams. So for instance, these 1, 2, 3, 4, 5, 6 rules actually imply all of the true identities between ZX diagrams. So you sort of get a lot for not putting very much in. Okay, so if I go back to this example, I can cut my gates open and start to apply these rules. They're pretty simple to see how a machine would do this. Dots of the same color fuse together. There's kind of a copy rule. Some more things fuse. Parallel edges fall off like this, and then, you know, at some point I'll get something much simpler, right? So I could do this with circuit identities, but I'd need a lot of circuit identities. Here I think I use three or maybe 4 different ZX rules to do this whole reduction. Okay, so this is quite powerful. If we want to scale it up, we need to think about how to do this automatically, right? And I guess the main, I should say we have a tool for this, automated reasoning with ZX diagrams. It's called PhysiX, pronounced like physics without the H. It's on GitHub. The main thing we use to automate this is we turn equations, which is like a 2-sided thing, into a rewrite rule. So we apply things in one direction. Okay, so this is a pretty good set of rules for working automatically with. And we can kind of massage this thing into a rewrite system. So One thing is obviously if I have a pair of dots, I should fuse them together. That gives me something simpler. This rule here, this is useful because you can see I've got 2 dots there and they get deleted, right? So that's useful. But how to deal with the color change? Something that you can do is you can say, well, it's kind of annoying to have red dots and green dots, so let's just make everything green from the start. Okay, so that means put Hadamard gates everywhere. And you can see there's kind of 2 kinds of edges in these diagrams. I have edges that don't have Hadamard gates and edges that do have Hadamard gates. So rather than having, that's a little hard to see, rather than having one graph with 2 different kinds of nodes, I have one kind of node and 2 different kinds of edges. Okay. And if I do that, I can turn this into quite a useful, effective rewrite system. Okay, I did a little bit of magic there and generalized these 2 rules. So if you know about these kinds of things, this is called pivoting and that's called local complementation. But they're basically rules that I can use to delete nodes out of these diagrams. Okay, so now I just take these rules and I apply them as much as possible. It starts deleting nodes out of my diagram. At some point, the rules don't apply anymore. I get a much simpler thing. Okay? And that's what happens here, right? So I can take a big circuit and I apply all these rules. And all of these rules essentially delete the kind of Clifford-like stuff in that diagram. So the things that came from Clifford gates, like C0, H, and S gates, go away. And the things that are left are things that come from non-Clifford gates. So this big circuit had a few T gates in it, and that's really what's left in this graph when we're done. Sort of one node for each of the T gates that was left in my circuit. And then we can try to extract this back out as a circuit. So if you're kind of careful about how you do this, you can always do this efficiently. So I'll just click through this. So here I took something that really didn't look like a circuit, and I can kind of move from the outputs to the inputs and sort of extract a circuit back out. Okay, so the first thing we applied this to was T-count reduction, and and it works. Okay, so you apply this thing, you simplify, and in the process, a lot of things which came from these non-Clifford gates kind of find each other and either combine to make something that's Clifford, or they cancel out to make something trivial, and you can get a circuit with fewer T gates. Okay, so in this case, I think there's something like 6 fewer T gates from the top to the bottom there. I know it's a little bit small. So we released this in, I believe it was March of 2019, and then a kind of a weird thing happened, which is another paper came out by Zhang and Chen at Alibaba, also in March of 2019, and they used the same benchmark circuits as us. I know it's very tiny, and they got the same exact T counts as us. Okay, so they did something that looks totally different from what we did, but they got exactly the same results. I remember a panicked email coming from them when they saw this paper on the archive, and they said, oh, we got exactly the same results. What's going on? We're like, we don't know. But we thought about this for a while, and a possible answer is that even though these techniques look quite different, maybe they're actually the same thing, kind of up to isomorphism. And this could be the case. So the main rule that we use for eliminating T gates is this thing called gadget fusion, which is we have these particular shapes of diagrams, which we call phase gadgets. It's like an unlabeled node connected to a labeled node. And if a pair of these is connected to the same nodes, they sort of merge together and their angles add. So if both of those were like T gates, they could cancel out with each other. If you know about things like phase folding you might have encountered if you do work in this space, or if I have Pauli exponentials, how their phases can add together and cancel out, this is sort of the same concept, but kind of witnessed as a ZX diagram. And actually, so Will Simmons also at Oxford wrote a paper relating sort of the ZX moves to the corresponding sort of phase folding moves. And it does look like these are the same thing, but the argument is quite complicated, and it's kind of depends on really exactly how you implemented this algorithm, whether you're going to get the same results. So another possible answer is maybe we actually just both did as good as possible, right? So maybe we both got the optimal T counts, right? Seems unlikely. I see people who know about this making a face when I say that. The reason that this is unlikely is both of our methods are efficient. They're polytime. Whereas we know even for diagonal circuits, T-count minimization is equivalent to this known hard problem, which is a least distance decoding for Reed-Muller codes. Well, okay, highly believed to be hard problem. Okay, so we don't believe that we did this efficient thing and then we actually got the exact optimal T-counts. That seems unlikely. But what if what we're doing is not actually T-count minimization? Okay, so our procedure knows about Clifford gates and it does something special with Clifford gates. But the way it treats T-gates, it doesn't really look at the angle. Okay, so this works just as well for any parameters here. They don't need to be kind of T-like. So in ZX diagrams, a T-gate makes a pi by 4 parameter here. It doesn't need to be pi by 4. It could be anything. So it's really dealing parametrically with these gates. And the same thing happens with phase folding and sort of phase polynomial stuff. So phases are kind of treated as black boxes, or at least the non-Clifford phases are treated as black boxes. In other words, they're treated as free parameters. So the same optimization would happen for any choice. Those didn't have to be T-gates. They could be any other parameter. I would have gotten the same number of them coming out at the end. So maybe what we're doing is not T optimization, but parameter optimization. So we can try to formalize this. So a parameterized circuit consists of gates from a discrete set and then also parameterized gates. So things which are functions of some input parameters. So I can think of these as functions from a parameter space into the space of unitaries. And we say that a parameterized circuit reduces to another parameterized circuit if there exists some function on my parameter space such that C1 of this set of parameters equals up to a global phase C2 of that set of parameters. Okay, so this is a reasonable notion of what it means for two parameterized circuits to be equal to each other. And we could say, well, maybe we don't want to consider all the functions. Maybe we want to consider a class of functions. And I'll say a little bit more about this class right at the end. But something we notice is all we ever really do is we just add parameters together. That's the only thing that decreases parameters. So maybe I should just consider circuits which are affine functions. So the new parameters are affine functions of the old parameters. And then I can say that C1 affinely reduces in that case. And also, something that it crucially uses is that parameters never get copied during this process. So I don't have an alpha on my left that becomes two copies of alpha on the right. So we can restrict this farther, and we can say, okay, well, first of all, we think that's hard if we actually copy parameters. We have some evidence for that. We can say that an affine reduction is parsimonious if it doesn't make copies of parameters. Okay, so this is just saying what that affine function is that's not copying parameters. And now you can say, you can define the problem, affine unique param count. We're given a parameterized circuit on a parameter space and an integer L. Decide if there exists a reduction to something of size L. Okay, so this is the decision problem associated with parameter minimization. I say, is there something that has this many parameters? And the theorem is, this can be efficiently and constructively solved. This can be decided. And the way you decide this is you actually just run physics. Okay, and it will tell you the minimum parameter count. Okay, so if I put Cliffords in, and then everywhere I have something non-Clifford, I just put a free parameter, and I run exactly the algorithm from the 2019 paper, it does get the optimal parameter count. Which is quite surprising. It's almost telling you that actually there is nothing better that we can do than just the super naive thing. Okay, so how do we do this? We This is basically just saying, what do? We run physics. And then this thing has the optimal parameter count. I think I'll have a, I'm quite near the end, so I've got a bit of a proof sketch here, but maybe I'll just kind of jump past that. A key point is that you can you can pull out all the non-Clifford stuff, and this thing becomes a stabilizer state connected to its non-Clifford stuff. And then you can reason about the stabilizers of that state to say, well, actually, there are no more reductions than the ones that physics knows about. Okay, so anyway, the paper's coming soon if you're interested in the details there. A couple of things that we're looking at now is kind of how necessary these assumptions are. So the affine assumption is actually not as strong as it seems. If you assume that the function is analytic, this actually implies that it has to be affine. So there are actually no non-affine analytic functions of parameters which result in genuine circuit equations. However, it doesn't, this thing, the sort of Euler rule, the thing that completes the ZX calculus, it's only piecewise affine, so it wouldn't apply to that rule. That rule doesn't count. And this parsimonious thing is kind of annoying, right? It seems less easy to justify. Now we have a proof that if you copy parameters and you do this and you ask the parameter minimization problem for ZX diagrams, which is the same as asking for post-selected circuits, that this problem is NP hard. So you can encode SAT if you do it with ZX diagrams. Probably there's a way to do this with circuits already, with unitary circuits, but we don't know how to do it yet. Okay, so those are the two big open problems. I mean, the title of this sounded like, hey, great news, we have a way to get optimal parameter counts. But the bad news is there's nothing better than what we've already come up with for minimizing parameters for circuits. So there's kind of two ways to see this. Anyway, if you want to see the paper, we tried to get it on archive by today, didn't quite make it. But it should be out next week. Yeah, thanks.
Thanks, Alex. Questions? Okay, I've got some. Can you explain a bit what is the actual restriction on the parameters? Like, they're unique, or like they occur once?
Yeah, so you could imagine that, so I have this parameterized circuit which takes a vector of parameters to a circuit. Now I'm rewriting that to another parameterized circuit. It can take a vector of a different length, so with fewer parameters, to a circuit. And you're asking what is the function from, r to the k to r to the l. And then you put a restriction on that function. And we say, well, it needs to be an affine function. But this parsimonious restriction is actually saying that there's only a non-zero entry in each column, one non-zero entry in each column of the matrix. And this sort of corresponds to one usage of the parameter from the left-hand side on the right-hand side.
Okay, but the parameters themselves can occur arbitrarily many times in the diagram.
No, because the length of the tuple is the number of parameterized nodes.
Right.
So it doesn't let you copy parameters.
Okay, so an interesting thing, which I'm going to not get right, is that a parameterized circuit which doesn't have many parameters, this has a simple representation in Fourier space. It makes it easy to simulate.
Okay. Interesting.
Any other questions?
Yeah.
So your parameterized gate is just the Z phase gate, right? And does the proof really much depend on this? But if you were to go to like a controlled rotation gate or something like this, does it still work?
Annoyingly, no, because the ZX diagram of a controlled rotation gate uses that parameter 3 times.
Yeah, that's why I'm asking.
Right. So it could be a strategy like this will work for controlled rotation gates, but yeah, it seems very somehow representation dependent. There is some representation dependency in this proof. It's really something to do with the fact that we're using ZX diagrams. So,
Right.
but it'd be good if we could talk about those, because those are used in VQCs all the time. So.
Thanks.
Just a curiosity, in the definition of a find function, you said that the matrix is composed of integers to mix the parameters.
They don't need, you don't need to assume that they're integers, but actually, once you have one of these parsimonious reductions, it happens to be that the only possible coefficients are +1 or -1.
Ah, okay.
So that follows.
Okay, thank you.
Okay, well, in that case, let's thank Alex for the talk.
Yeah, how do I do this? Into settings.
What are you seeing?
Like a cloud on a method.
Did anything happen?
Yeah.
Good. You do see my slides though, right?
Yeah.
Okay.
We solved the problem at this end.
Okay, we're okay. What's that? We're good. Okay.
Okay, great. So the next talk is from Lucas Stinchcombe, who is from Simon Fraser University. Please take it away, Lucas.
Thanks. So this is joint work with my supervisor, Matt Amy. It's titled Polynomial Time Classical Simulation of Rottler's Shifted Bent Function Algorithm, which is a little bit of a mouthful. So I'll call it the hidden shift algorithm, which is what it's called in the literature anyway. So some background, the hidden shift algorithm was originally devised as an Oracle algorithm in order to give query complexity separations in the classical and quantum cases. Since then, it's been used as a benchmark for classical simulation, where the Oracle is given an implementation. So classical simulation is just, this is the room where everybody knows what that is, but quantum circuits and simulating that classically. So then, since then, it's due to some empirical evidence, it's been conjectured to be classically efficiently simulable or simulatable, whatever you want to say. And so in this talk, we'll actually show that this conjecture is actually true by giving a polynomial time simulation. So the way we'll do this is
we'll take the circuit, we'll cast it to a sum over paths expression, which is like a formal expression that captures the action of the circuit. And then we'll give a rewrite system that's confluent for these expressions, and then use this rewrite system to give a straightforward simulation algorithm. So the setup is just to understand what the hidden shift algorithm is. We'll start with a vector space of functions from n booleans to the reals. We can see that there's like we can have potentially many bases, but we can single out two bases for this vector space, one being like a Dirac delta. So given an S here, it will output, the function will output 1 if and only if the input is exactly that bit string. And here we'll compute the parity. Given an S. We'll compute the parity on the bits that are indexed by that S. And so for any given function in the vector space, we might write it in this basis by just taking the points of that function. And over here, we would just do, this is a little bit more interesting. These are Fourier coefficients for the same function, and we can get those by a Fourier transform. And so a Boolean function in this space would be called, or a function in this space would be called Boolean if its image is in -1 and 1. And if if f hat here, the Fourier coefficients are also a Boolean function up to a scaling by a constant, we'll call this a bent function. So multiplying by this constant square root of 2 to the n, we get the dual function, which is also a Boolean function. So we know what bent functions are. We might want to actually construct them. So the way we would do this is just get an arbitrary Boolean function on half the inputs and an arbitrary permutation on half the inputs, and just apply this construction called the Mariano-Macfarlane bent function construction. And this can be just checked to be a bent function with the dual that is closely related. And so we'll call the set of these functions capital M. So now we're in a position to actually compute or actually define the problem of the hidden shift. So given a bit string S and a bent function in M, we'll call G the shifted function, which just computes F shifted by our bit string S. And then the hidden shift problem is just to compute S given an oracle which hides this S. And what does it mean to hide it? Well, we might have two different variations of an oracle. One which gives access to the original function f, its dual, and the shifted function, and this red oracle here that might give access to the original function and the shifted function. And so here we have query complexity separations in these cases, and interestingly, in the red oracle case, we have a time complexity difference that is just the result of we can do relative to this oracle, p does not equal BQP, because in the quantum case, we can extract this shift in polynomial time versus classically we need exponential time. So the red oracle is not actually that important for this talk, so we're going to talk about the blue oracle here. This has been used in simulation benchmarking with this circuit, where the oracles are actually implemented over this particular gate set, and it doesn't really matter the specifics about this gate set, but the important thing is that the number of controls here on the Z's are fixed by some fixed M. So here, these oracles would compute the G, which is the shifted function, and the dual into the phase, and in previous works, without exception, M has been equal to 2. And the reason for this is because the CC Z gate can be implemented with some fixed numbers of T gates, and so they wanted to control the number of T gates in their benchmark. And an important thing here is that this actually bounds the degree of these, the polynomials, the bent functions that are computed by at most m plus 1. So in the m equals 2 case, we have at most 3, degree 3 bent functions. And then Julian Codsey conjectured this to be polynomial time simulable based on empirical evidence in 2022. So maybe we'll just talk about correctness here. So we'll just take the case where S is equal to 0 and pi is the identity. Well, we can just observe the action of the circuit on the 0 state. We get an expression like this. We know what F is because it's a bend function, so we'll just actually plug that in. And then some simplifications where we just notice that we have some constructive interference when two variables are equal and destructive interference when they're not equal, and we just resolve this to be the shift, which is just the 0 state. So what we just did kind of hints at maybe a possible way to formally express this. So we're going to define the sum over paths formal system. These look a lot like what I just did, but these are actually just formal expressions where S is a complex number, V is a set of indeterminates, and these P's and Q's are polynomials, Boolean polynomials. And yeah, Boolean polynomials just being polynomials over F2, where for every variable, V squared is equal to V. And so we come to a proposition that we can actually, over our gate set, we can compute the sum over paths expressions in polynomial time, and the expressions themselves have polynomial size. And by polynomial meaning in the volume of the hidden shift circuit. And actually, we can read this as actually the size, the number of gates in the hidden shift circuit, because each qubit has at least one gate acting on it. And this is, again, just due to the fact that we have a bounded number of controls on our Z gates. So this will polynomially bound the size of our expressions, and then each tensor product or composition we use to construct our expression will also take polynomial size in the expression size. So some examples here. Let's take a Bell state circuit. You can kind of think of this as a contravariant functor of sorts where the orders are reversed. And let's just use our composition and tensor rules that come with the sum over paths expression, or sum over paths formalism, and we get some expression like this. And so we can actually evaluate this expression if we wanted to by just summing over these variables over zeros and ones, and we would get a linear operator which is the same as the linear operator that we would have gotten if we just interpreted the circuit directly, so everything's sound and we're happy. And then another example, so two Hadamards, we'll just do the same thing. We do know that two Hadamards just has a circuit identity, which is just the identity itself. And so we need something the same, just like in the ZX calculus, where we would simplify this into the identity. So we need some kind of rewrite rule similar to how we have circuit identities. So for this, we'll introduce the HH rule, but not just, maybe some of you are familiar with the HH rule, but we'll allow something called the simple HH rule, which allows this simplification that we were just running into, but in the general expression of this rewrite rule will limit the number of variables that are being substituted to be at most one. So what this means is that here, if you look at this expression on the left, we get the expression on the right by multiplying by 2 and substituting z and for y. And this is a valid application of the simple HH rule because z is just one variable. But we won't allow things like substituting z plus w into y. So, and just to fix vocabulary, we'll just call this an application of the simple HH rule with respect to x, where x is the variable that we're kind of factoring out of the expression. And importantly here, we've reduced the number of variables by 2. So here we have 3, now we have 1, and it's more simple than before. So we'll come back to the hidden shift circuit. We had our circuit, which is used for benchmarking, and we'll, in polynomial time, construct the corresponding sum over paths expression. And it has this kind of hideous shape, and it looks not great, but one simplification we can do is that we had this pi parameter in the, which is a permutation in the construction of the bent function. So we can actually just ignore this by relabeling variables through like an isomorphism of rings, if you want, if you will. And I'm kind of sweeping stuff under the rug here, but basically we can just move stuff to the state, and there's no rule that cares about the order of the variables in the state, so we can take pi equal to the identity. And so at this point, great, we have this sum over paths expression, like what can we do with this thing? Well, naively, we could just take our rewrite rule, of which we only have one, and just apply rewrites until we can't, and then finally evaluate this sum over paths expression by just summing over the variables. So this gives us kind of two problems. One is that the evaluation has cost exponential in the number of variables, because we're summing over two values for each. And the other one is, okay, how do we choose a rewrite to apply? So we want to simplify this before we get to a point where we would be able to evaluate it, but we don't know what order we would apply these rules in to get what we want. So number one is actually solved because I briefly went over the proof of confluence. Well, that proof was actually just a sequence of simple HH rewrites, which means that there is a rewrite sequence that gets us down to the final state that we're interested in. And the final state, if you notice here, has no variables, so the evaluation is trivial. And so number two, we can invoke a little bit of wishful thinking and hope that every sequence of rewrites actually completely simplifies our expression down to the final state, which is the result of the hidden shift circuit. So this is actually the property of confluence. And so we'll just say here that A rewrites to B confluently if for all C and D such that A rewrites to C and A rewrites to D, we have that C rewrites to B and D rewrites to B, which is just to say that whatever you've done in the past, there's always a way to get back down to the final state. And so you can just forget about what you've done before. So here's an example to sort of see what sort of degrees of freedom we have in choosing a rewrite. So let's say that we want to apply a simple HH rewrite with respect to X. Oops, sorry. With respect to X. So what we might do is rewrite, so apply a substitution where we substitute W in for Y, or we could potentially substitute Y in for W. And the question is, well, does this matter? And intuitively, it would seem like not. And intuitively, you would be correct that, yeah, if substituting Z in for Y rewrites to S confluently, then substituting Y in for Z also rewrites to S confluently, and vice versa. So with that, I think that will basically be enough to just get what we want here. So we can do now just a case analysis, basically, where we've noticed that in our expression we had this variable set. We can easily just show that all rewrites will be with respect to the first 4 variables for each I. And just to give an example of how this proof works, let's say that we considered only rules with respect to xi and zi for some I. Let's look at the potential rewrites that occur as a consequence of this. So we'll take these relationships here, which are the basis for the substitution. So we're going to juxtapose these here, and we'll notice that, okay, this zi rule cannot be executed because it has too many variables, and so we have no choice but to execute the xi rule. So yi gets wi plus the shift. And after this, we track what happens to the other rule that we had, which is the zi rule. And so here we'll notice that actually what happens is this linear sum gets added into the lower linear sum here. And so now at this point we just have one variable and we can just do the corresponding rule for zi. And we've annihilated both rules. So what this simple little simplified example tells us is that we have a dependency between rules. So we have a dependency of zi on xi. And in the similar way, we can just expand this to the rest of the rules that we had. So we can see, we can just do the same thing. There's a little bit more complication with respect to the other rules, which are, I don't want to confuse anybody, these are just the same simple HH rules, but taken with respect to different variables. It's a little bit more complicated here just because we have potentially nonlinear terms, but we can just do the same sort of strategy and find that there are dependencies between these rules that we have to execute. And we come to a claim here that, okay, so every valid rewrite sequence has to satisfy the dependencies that we've constructed, and every rewrite sequence which does will terminate with the final state S, which is the result of the quantum algorithm. So then, at this point, basically the two problems that we raised, the number of variables and the choice of rewrites is solved. So we can just write an algorithm which does exactly what we want, which is just to take our hidden shift circuit, turn it into a sum over paths expression in polynomial time, and apply these simple HH rewrites until we cannot anymore, at which point there are no variables, the evaluation is trivial, and we just return the result, which is the exact shift. And so the theorem is algorithm 1 simulates a hidden shift circuit over gate set G and polynomial time. And this is generic in the sense that there's nothing that cares, there's no analysis of an algorithm that happens here. And in principle, this can be done with any circuit, just without a guarantee of efficiency. And so we have open questions, whether this method works for other sum over paths expressions. In particular, we had here a quantum deterministic algorithm, so whether it's effective for non-deterministic algorithms. At the end, we would have to do some sort of sampling, but whether it can be augmented to handle these cases. And then the other question is, okay, instead of having a simple HH rule, what if we allowed linear or affine substitutions in our HH rule? How does that affect the property of confluence? And that's it. Thank you very much.
Okay, thanks, Lucas. Do we have any questions?
Thanks for the nice talk. Is the HH rule, so you're just applying the HH rule, right?
Just the HH rule, yeah.
And that's always terminating, is that right?
Yeah.
Because you remove a variable.
Because we're always removing variables. Yeah.
Okay.
So it's noetherian if you care about these terms. But
So that theorem you had that said all of my terminating, if my path terminates, it terminates with S.
Yeah.
It's actually that all paths terminate.
all paths do terminate, but all paths terminate with S is the main part of it.
I see.
Yeah.
And the... Okay, no, I've forgotten the second thing. I'll ask you at lunch.
Okay,
But
no
anyway,
problem.
thanks.
Cool, thanks.
So I know you put this in your open questions, but what is do you know any example of a larger class of expressions that is similarly efficient to reduce?
That's a good question, and that's something that we should be doing. But there's like obvious stuff, like I guess the Bernstein-Vazirani algorithm, but those are easier. So we haven't really looked at other examples. The question that we're really asking is whether these rewrites are confluent in general. So if we can write it in this sort of flavor of this flavor of sum over paths, we're trying to figure out whether we have confluence in general, not just for these expressions. Yeah.
Last question? No. Okay. Thanks very much.
Thank you.
This side, is it? Magic. Amazing.
Okay. And next and final talk for the session, Alexander Bernstein from Pascal.
Yeah, thanks. Yeah, I'm Alexander. I'm here to present work on Cadence, which is, I say, a domain-specific language for quantum computing, especially for what we call this digital analog paradigm. And this is a sort of high-level talk in terms of the language, and you might be interested to know that this is now also the main framework for quantum computing that we use at Pascal. So there's been a lot of, let's say, user-friendly choices taken as well. Quick overview is that we'll basically first just cover the definition of what we mean by digital analog, especially the analog part. I think it's quite probably unfamiliar to much of the audience, and then we'll effectively walk through the different parts of cadence. So to begin with, to be sure that you know everyone's able to follow, we view quantum from the point of view of physics. So we think of a quantum state that evolves through time. So a quantum system in that sense then is described by the Hamiltonian, which is basically the energy of the system, and the sort of evolution through time is then expressed by the Hamiltonian operator, and that's what we say that we are programming. If you were here throughout the week on Thursday, there was a talk on SimiQ, which is kind of following a similar idea, even calling it Hamiltonian oriented. So, to begin with the distinction between digital and analog quantum computing, we say that in digital we think of discrete actions, whereas in analog we're thinking that we're programming this Hamiltonian continuously in time, and that by an analog device we mean something which has a native execution of the time evolution of the Hamiltonian. And this is quite possibly trying to do something of practical importance with quantum computing, quite possibly superior in the short term at least, and so the idea is basically with digital analog quantum computing that will try to take the best of both worlds. We'll work with, let's say, single qubit gates from in the digital sense, and we combine this with analog entangling operations. And some people have shown that you can think about quantum computing in this way, and it still turns out to be universal. Right, so we're a hardware manufacturer. That means that we obviously have what we build in sort of most important object. So our device follows this Hamiltonian here. The exact mathematics is not very important, but basically we end up having this programmable laser pulse which acts on all qubits, and that we have a programmable register, at least, like a reconfigurable register, which only acts between neighboring atoms. This Hamiltonian has the shape of a Ising Hamiltonian, which is something which physicists get very excited about because they spend many years studying this model, and there has quite a lot of applications also, modeling systems in this manner. In particular, graph problems that you can, we say, natively embed into this Hamiltonian. So that's the kind of applications that primarily targeting. So why do we choose to build a new quantum framework? Don't we have enough? Well, in the digital sense, yes, both high level and low level. In the analog, there's less, and most of them are really targeted towards programming a specific device. It's it really requires that you understand the physics of the device very well. We'll see an example later. Alternatively, now we have this sort of high-level SimiQ approach. Unfortunately, it's very quickly that you end up with a laser pulse, which we cannot currently execute, and be true to the program that's written. As such, we've introduced cadence, and it's differentiable, so we work mostly with variational quantum algorithms. So you have some parameters, you execute a program, and then you want to run a loop where you calculate the derivative of your parameters, and you want to update them. We work in the quantum circuit model, and we say that a circuit is composed of blocks that corresponds to operations. Now, in the first bit, what we'll mostly talk about is this type of block here. This is the time evolution operators. This is an analog block, and we'll talk about the rest later. So, in some sense, this is the key idea of Cadence. It's that we try to, remove ourselves from this really hardware physics point of view of programming the laser pulses, and we try to, abstract that for our developers and think in a more quantum information theoretic manner that they're more accustomed to. As such, well, first and foremost, we have some concept of dimensionless units that we can then compile into what the hardware wants to do. This is work in progress. In particular, time is still a real unit. We'll talk about the syntax later, but we compose operations through time, and we separate out the different terms with the Hamiltonians. In this case, we can rotate in the x direction or qubits, and then we can have this analog interaction where you kind of entangle the system according to the register, which is again going back to before is how we can maybe solve graph problems in the analog model. So compare this to Pulsar, our other library. This is really how it looks like when you're programming current analog devices. You end up having lots of numbers floating around which are really tuned to the values that the device takes, and you have to understand, again, the physics of the device, and you end up having, this is the program being realized, and you have to experiment your way towards finding the correct time to do things. This is not very important, but again, compared to this approach here, it's, we're hoping to develop something which is, slightly higher level. So on to the key parts of Cadence. Working from the top down, on the outer layer, we have this quantum model. It's effectively thought of as an abstraction of the backend. So a backend can be a QPU or a numerical simulator. And as a sort of key point of view, we think of this as encompassing a whole hybrid quantum classical program, again, variational algorithms. And for convenience, we've built this on top of PyTorch, the machine learning library. So we'll see later we can have, differentiable programs, and it's very user-friendly, to at least to our developers, and it really represents, the compiled executable program that can be done on the device. And well, in this case here, we've assumed the existence of a circuit. We've just made an observable. You often end up evaluating the state against an observable in variational algorithms. Right. So, and the model has, functions like calculate expectation values, sample, run. We also have domain-specific quantum models for specific algorithms, or also to provide convenience functions like tomography, say, right, to recreate the state from bit strings. The next level of abstraction will be quantum circuits, taking the fairly normal definition of a quantum circuit. It really encapsulates the quantum computation part of the program, and we've decided that, for us, quantum circuit is really a final step. We're decided that once you made a quantum circuit, you're supposed to not do anything more with it outside of having it run, in the program through the quantum model. All right, so how do you make a quantum circuit in Cadence? You need a register. Again, for our device, it's quite useful to be able to just have a graph with positions and put them in. As such, we've developed these abstractions. But we can perhaps talk more about the blocks. So we say that quantum operations are blocks. They can be parameterized. We have like a distinction between primitive blocks and composite blocks, where primitive blocks represents, if not hardware executable, then these, kind of a real quantum computation. And we were inspired by, sort of functional programming approach when you compose the program. So we say we chain them through time, or we cron them in parallel. When you're doing with analog quantum computing, you can't rely on the compiler to figure this out for you, unless you really have a super high-level language. And you can add blocks, because you also use blocks to create Hamiltonians. So, we see this here on the picture as well, that we have, in this case, digital gates. We can have analog operations. We can have these sort of digital analog operations, and we can combine them, and they're all, a block. And the blocks are, relying on being executed according to the register. So we think we might have some cool possibilities to do there by combining those when you program. And yeah, symbolic parameters. This is a very key abstraction for us in practice for our developers. So let's see. So one of the blocks is a Hamiltonian block. So here it's basically, this in some sense is this Hamiltonian-oriented programming approach, where you can, define a Hamiltonian. This is just a sort of initialization function. You can supply a register. You can supply a custom Hamiltonian that you write using the block system. We also, of course, apply sort of standard Hamiltonian, like the one that we can execute on the device, which you can then modify with the, interaction strengths manually. And yeah, this is, I think, one of the key challenges if you want to really write a digital analog quantum program and do something which you can't do with a different abstraction, is going to be that we'll have to be able to write, any arbitrary Hamiltonian like this and manage to compile it or do this, what we call a digital analog transformation into the system Hamiltonian. So this is a quantum machine learning circuit. This is sort of our main in practice type of program. So here you see a little bit how you could create a very basic program. You compose in parallel, so acting on all qubits, digital gates, because then you can encode the data in each qubit and have, sort of different parameters in each qubit. Otherwise, you're really losing a lot of expressibility. You can then create a register based on the problem topology, again, to leverage this analog evolution. And we can have, this variational ansatz, which is typical in variational algorithms like VQE or quantum machine learning, where you can supply the analog operations, which, of course, you can specify, which qubits this will act on. So you end up having a bit of flexibility in experimentation. And then, yeah, you compose that in the circuit. And this here is really what we hope is executable in the near term on our devices, which could be exciting. As you might have seen, neutral atoms devices are growing in size quite rapidly with a lot of restrictions. This works, like a quantum model, works as a PyTorch model, as I said before. So you can put this into a optimization loop based on PyTorch, and it all works nice. It's natively differentiable, which means we just overload the PyTorch automatic differentiation engine. So some of those methods you can use on hardware. Of course, that means that you execute many circuit evaluations, because by this what we mean is you want to have a parameterized quantum circuit, you want to calculate the derivative of one of those parameters, so you end up having to execute a parameter number of circuit executions times your shot count. And we have implemented this more general parameter shift rule, which will allow us to not just take derivatives of simple operations like the digital gates, but also more complex digital analog operations. So I'm going to skip ahead to this slide here, since we have time. So as I said, this digital analog approach it can turn out to be universal in some limits. So this is actually a quantum Fourier transform. I'm not going to be able to cover it in much detail, but this is how you imagine that a more complicated circuit would look like, and it shows some of the key ideas of the paradigms where you have, we talk about generators, so like an sort of a Pauli operator generates parameterized Hamiltonian operation. So instead of having C-phase gates, you would end up having this analog interaction, which you'll have to compile using this digital analog transformation ideas. And yeah, this is just quick. Just skipping back to the summary. Focuses on building programs which are executable today or in the very short term for our developers to use, day in, day out. For analog, digital analog, and digital analog modes, and that it's sort of trying to move away from thinking about physics, I guess, really working in the opposite direction of what most people here work in. Higher level interface, really borrowed from this Julia Yao and Kuiper, the idea of blocks and composable circuits. I think this is a great way to, in the near term, build a larger program, and it's all differentiable. Future work, we'll be working on trying to open source more of our internal libraries built on top of Cadence, so that will further enrich the syntax according to problems. Compilation, one thing which will be very interesting is that the register on Atom devices is reconfigurable during execution. So you can imagine composing blocks with different registers, and the compiler will have to realize we will have to, move the atoms physically in the device between stages, and also work on these transformations. Thank you very much.
Okay, thanks, Alexander. I'm having the first question. This system, if I understood right, you can do a register of any graph, and you can have any interaction on the edges. So it seems like a great system for doing measurement-based quantum computing. Have you looked at that?
Not personally. I know we have people that have worked in this direction. We've not really said anything about it publicly, so I think I'll have to leave it at that. I have some colleagues in the back. I don't know if they know anything we can say. Yeah. Very, very early stage research.
Any other questions? Oh, sorry.
Yeah, I have a kind of a vague question about what's you kind of foresee people interacting with this. So the point is to kind of get the physics knowledge kind of out of this, so you have developers interacting with this system. Do you think there's a right level of abstraction that a developer who doesn't understand the physics can really understand well enough what this analog step is doing in the computation that they can use it in an effective way?
Yeah, I mean, this is really the key idea that we're thinking about with this analog rotations is that, well, okay, maybe, for analog, you really will require physics knowledge, but at least maybe you can have, a general introduction to quantum mechanics course and not, a full master's in optical, like sort of manipulating atoms with optics. And yeah, in terms of, that's also the point of the block system, right, is that we think maybe you can more easily write programs for, an academic group in Germany in spring managed to have 10,000 atoms trapped in a single device. So we're potentially looking at that level of atoms in a very short term. 5 years ago, no one was doing neutral atoms. So we're really just trying to scale the computation model step by step. We'll see.
So how specific is this to your hardware, and are the ideas here applicable to both other like neutral atom systems and to the ion trap and superconducting qubit devices?
Right. Yeah, I think I had planned a sentence that I skipped. It's definitely applicable to other neutral atom systems, especially the ones which have an analog mode. So that's occur at least. Yeah, I mean, we can definitely write the sort of compilation step of translating this either via trotterization to a fully gate-based basis, or if we can get the, the pulse-level access, say, through superconducting hardware, then you will have the possibility to realize Hamiltonian. Just so happens that, yeah, neutral atoms have at least using Hamiltonian, so it's kind of into, like, easy to start going, whereas I foresee other hardwares at the pulse level, which is where we're currently mostly working, is significantly harder. But if we have time, we'll definitely explore it.
I see, yeah. As I understand it, there's, nothing is natively using gates. It's just a question of whether or not they're exposing their pulse interfaces.
Yeah, exactly.
Thank you.
Last question? No takers? Okay, thanks very much, Alexander.
Thanks.
And that's lunchtime. The next session starts at 2 o'clock.
model or uniform quantum circuits. So quantum circuits that can be described by some polytime deterministic Turing machine. And so the fact that these two models were kind of equivalent in the sense of defining the functions that can be efficiently computable in the quantum model kind of inspires the work of implicit computational complexity. So the background on this is the work of Bellantoni and Cook that provided a schematic definition of classical polynomial time. So in a sense, a set of functions that have no extrinsic bound in terms of time or computational complexity, but in the rules of how we can construct them, they are sound and complete for polynomial time. And this also in the quantum space also inspired the work of Dalago, Manzini, and Zorzi, and also Yamakami with implicit definitions of quantum polynomial time. So either with quantum lambda calculus or with a function algebra, for instance, with a boundary recursion. And we also did some work on this with a quantum programming language. They also had boundary recursion kind of inspired in the work of Yamakami. And so the usual way that this works is we give an implicit description of so for instance, like a programming language, how we can build these programs, how do they behave, and we kind of show that this is sound and complete for instance, like the quantum Turing machine model running polynomial time. But this can also have interesting applications in terms of circuits. So even though the proof is not directly towards uniform quantum circuits, there are interesting things that we can do about this. And it turns out that, for instance, the link between the implicit description and the uniform quantum circuits is non-trivial. So in 2022, Yuan and Carbon, in their paper trying to describe data structures that work in quantum superposition that are efficient for quantum algorithms, they kind of run into the problem that they call branch sequentialization, which is the fact that kind of in a Turing machine model of algorithms, in the way that we think about it, the quantum control, when it, in terms of the branching, we expect the complexity to be the maximum of each of the branches, and that in the end they will interfere with each other. Whereas in the circuit model, in a sense, we have to kind of compute one of the branches and then the other in succession. So we're kind of forced to add the time complexities instead of doing the maximum of each. So in their work, they have to restructure their program to do the same thing, but try to avoid this slowdown by using an oscillus, for instance. But they kind of point to this problem that in time complexity, there's this problem. So there's kind of this question of, is there a compilation strategy, for instance, that we could have a set of all polynomial time quantum programs that we know that we can compile them into uniform quantum circuits, and this is kind of to give an idea of how these ideas can be kind of applied into reasoning about circuit complexity. So in our paper with the quantum programming language, we give precisely a way of compiling these things into circuits that are bounded in polynomial size, which is what's indeed not a trivial construction. And so this work is on kind of a new approach, or a kind of a different approach from the previous one in terms of talking about quantum polynomial time. So we start by trying to mix two different lambda calculi. So we start with the dual lie-defined logic, which was a lambda calculus developed by Bayo and Terwi, where they have types that they that kind of keep track of when we do duplications on, or when duplication has occurred. So for the people who are interested in intuitionist linear logic, so we have here the types, and we have like a linear arrow, and the nonlinear arrow kind of corresponds to the bang on the A, which means that A is a type that we're gonna duplicate in the expression in B, and the par A means that the term has had some duplication done to it, and we have the normal polymorphism, and this calculus is polytime strong normalizing, and it's complete for all polynomial time functions. So this is classically. So our idea of trying to give a lambda calculus definition of quantum polynomial time is to kind of take this calculus and try to include quantum operations on it, and to try to obtain like a stronger calculus in the end. And so, for instance, like an example of how this works in terms of bounding to polynomial time. In Delal, the church integers have this type where we have a nonlinear arrow and we have a par symbol on the right, which means that the term has some duplication on it. And so, for instance, like the integer here is some function that we're going to duplicate. So we're going to have n copies of it. So that's why the par is there. So we can do addition, multiplication, and in a sense, we can, for any polynomial, we can create a term that will have a type, which will have a number of pars corresponding to its degree in some sense. And so this is how we can build every polynomial. And it also is kind of safe in the sense where you cannot do anything that's exponential with this calculus, because every time we do some duplication, the par kind of forbids the term from being an endomorphism, so we cannot iterate duplications. So it prevents exponentiation. And so to try to quantize this calculus, you take another one, so developed by Alejandro Diaz-Caro and Otavio Malherbe. And this is a calculus that's very strong in terms of computational operations. So it's sounding complete for single qubit unitary transformations. So I give here like an image of the grammar of these terms and the types. But basically the idea is that we can define booleans and qubits with a sharp representing superposition of some type. And 1 qubit gates, for instance, are from sharp B into sharp B, so superpositions of booleans into superpositions of booleans. And so we have let and match, and we have these ways of building the gate. So for instance, we can build the C0 gate as a let that then matches all of the different possible terms. And then we can type this with a sharp, a pair of booleans into sharp pair of booleans. So two booleans possibly in superposition into to the same thing. So our idea is to mix these two, and we call this the PLanQ programming language. So we have the P for polynomial time. So all the terms are evaluated in polynomial time, and that we want that all quantum polytime functions will have a corresponding term. So we want to be sounding complete. And we also have the fact that we want to be unitary, so quantum also, and all operations are unitary, so we cannot kind of mistreat qubits even in like hidden ways with weird types. And we want that any quantum gate has a corresponding term to it. So the syntax of PLanQ is we have cat 0 and cat 1, we have variables, we have if then else, applications, abstractions, pairs, and the pair destructor. And we have also, for any term, so then the sense of this will be, I'll get into it this later, but technically for any term we can build a superposition of terms. So we can, for any possible term, we can consider a linear combination where the coefficients are complex numbers. And so we have also a typing system where we have the booleans, which are the types of 0 and 1. We have linear applications, nonlinear applications, as in Delal. We have pairs and the sharp representing superpositions, the pair to the par symbol to keep track of duplications, and the polymorphism. And so this is the set of rules is kind of a combination of lambda S1 rules that ensure unitarity when we deal with qubits, and we also have Delal rules to make sure that we cannot iterate over polynomial time. The fact that we have so many rules is kind of a result of the fact that we have, for instance, a classical if and a quantum if. We have two different types of arrows, so nonlinear where we can have duplication and linear arrows where we cannot. We have quantum pair, like kind of pair the structures that can safely handle superposition, but other ones that are more general when we can only use like booleans, for instance. So we have kind of these different techniques that we can use, which are interesting, but in the end, it also looks like a lot of rules, but it means that it's expressive in the sense we can do a lot of stuff. And so in terms of the properties of PLanQ, we can show subject reduction. We can show that for any kind of constant size, at least for any like n entry qubits and k output qubits. So consider like this type here on the right, we are sounding complete for all of these qubit transformations. So in the sense, sounding complete means that we can do any unitary transformation. And also these n and k coefficients have the property where if, for instance, k is larger than n, then the term behaves as an isometry, so it'll preserve in a product. If k is precisely equal to n, then this will be a unitary transformation. And we also have that if k is smaller than n, then this would represent qubit erasure, and in fact it's an uninhabited term in Punk, so it's not something we could type. And we do this with a realizability model, so we kind of, for each type, we can talk about like what are the possible terms that would correspond to this type, and we prove that the realizability model is sound for the typing rules, and so we can kind of reason in a simpler way about what terms would correspond to each type. And so in terms of work in progress in this, we don't have yet a quantum polytime completeness, and we'll get into why that's harder than it looks. But first, I'll give some examples of typing in Punk. So for instance, to say that the plus and minus states are indeed qubits, we first state that the ket 0 is a Boolean, the ket 1 is a Boolean, and that they are orthogonal. So we have kind of this notion of orthogonality for types. So given a type, we have some definition of what it means for two terms of this type to be orthogonal, which for Booleans and qubits is okay, but if we get into more complicated stuff, it makes the language, kind of undecidable in the sense if we're talking about like orthogonal functions and orthogonal any possible term. But for Booleans and qubits, it's rather simple. And then we just check that the coefficients, that the sum of the squares of the norms equals to 1. And so this says that indeed plus and minus are superpositions of Booleans, or more simply qubits. And so, for instance, to define the Hadamard gate, we can do this. So we can have that the plus and the minus are indeed qubits. They are orthogonal. And then having some qubit variable, we can use it in the if. So the fact that we are using the qubit variable in the guard of the if forces us to check that the plus and the minus are orthogonal. So if indeed we are using just a Boolean value, the two branches could be the same. We wouldn't care. But since the guard of the if is a qubit, we check that it's orthogonal. And then we can just use subtyping to say that a superposition of a Boolean is just a superposition of Booleans. And then we can close the application, and we have the Hadamard gate. So this is kind of how we can construct gates. And so kind of difficulties of the interesting part of this is that we have in Punk two different contexts. So we have a linear context in the typing, we have a nonlinear context, as in the LAL. Differently from the LAL, we don't have a full weakening. We only have weakening on the nonlinear context, because the linear context is where we would want to be strictly linear, because it's where we handle qubits and other types of data types. And so we have linear applications and nonlinear applications, and we have linear abstractions and nonlinear abstractions. So in the linear application, nonlinear application, we can admit at most one free variable in the thing that's going into the application, and this is kind of just to prevent kind of hiding variables inside the term, which is going to be treated non-linearly, and to prevent exponential stuff. So it's kind of more on that regard. So if there's any variable free in the expression going into the nonlinear abstraction, it becomes nonlinear. And then this is interesting because when we close nonlinear variables, we transform the type. So in a sense, we could have some qubit type that was in the context that we treated nonlinearly somehow, and so far so good. It changed sides in the typing context. But once we go and close this and say, okay, now I'm going to define a function based on what I did to this qubit, the typing discipline forces us to say that it's no longer a qubit. So we have a bank function, which is not a modality in this case, just something that transforms types. And so it's something that says Booleans, it's fine to copy. Functions, it's fine to copy. We can treat quantum gates non-linearly. You can copy them as many times as we'd like. And a pair is, we can copy it if we can copy both parts of the pair. And obviously superpositions, we do not allow them to be kind of copied or cloned. So this kind of, we prevent even in the nonlinear arrow to do like stuff that's nonlinear to qubits. And so in kind of mixing these two typing systems, we can do like Del style iteration with the lambda S1 term. So we can have some gate G, and we can iterate it a polynomial number of times into like a polytime quantum random walk, for instance. And this works fine with no problem. But kind of the difficulty that that we may have is talking about lists of qubits. So lists in Del or polymorphism. So for instance, like a list of booleans will be will have this type. And to reason about lists of qubits or superpositions of lists of qubits is very tricky, because now we have to say what does it mean for two lists to be orthogonal. So given the type of the list, given a polymorphism, we have to start thinking about orthogonality of polymorphism and orthogonality of functions. And this was kind of the first direction we were going until we saw that this is actually kind of hard to think, because kind of the first approach was, okay, two lists will be orthogonal, so having this type if for any type that I give to them, or any closed type or polymorphism free type, then they'll like inductively satisfy the orthogonality condition for the new like type that I give now that I've given X. But then we have to reason about orthogonality of functions, and then that's very. So we also had the idea of superposing functions, and then we saw that that was indeed very restrictive. So for instance, like if we have two unitaries of the same dimension, for them to be kind of orthogonal, we would like for them to have orthogonal outputs on given the same input. So if you have a superposition of f and g, if we give 0 to the superposition of f plus g, we want f of 0 plus f of g to be a safe kind of superposition in the end, and so they have to be orthogonal. And this is very restrictive, so there are no two kind of unitary gates that would satisfy this. But if we start talking about isometries, then it's okay. But it's a bit tricky, and then we don't know like how much expressivity would have in the end. So this is kind of the roadblock so far. But yeah, so yeah, I'm happy to talk more about any of these things. I kind of went quickly, but if you have any questions, I mean, we have this version on the archive that we're still working on a new version, but I'm happy to take questions. Yeah. Yeah.
Yeah, that one. So the completeness up there is a different kind of thing from the completeness.
Yeah.
Right? Could you explain?
Yeah, the difference. Yeah, so in a sense, if we consider any kind of fixed dimension unitary transformation, so something that we can, so it's something that we can just create a term that satisfies it. That's easy to do, easy enough. Quantum polytime completeness, we would like, for instance, to have some list or a function that would take some list of qubits of arbitrary size, and that would be able to iterate over the list and to do like operations, so not having any fixed size entry in the term. So in a sense, okay, for any arbitrary dimension, we can define any quantum gate of that dimension in terms of having just some input and to be able to iterate over it and have a general term for that. It requires using lists, for instance, and it's tricky to think about superpositions of lists given the Del types.
Okay, so this first completeness, it's kind of like a fixed parameter thing. If I fix
Yeah.
a parameter, then I can sort of two syntactic things are sort of equal if and only if the unitary is the same. Is that?
Yeah, it's the soundness and completeness here. So more precisely, it means that given this type, so between but from n qubits to k qubits, for any isometry, we have a term of this type that behaves like the isometry, in the sense where we give it the input and it'll reduce to the correct output. And any term of this type behaves kind of like this. So if it has the dimensions to behave like an isometry, it will. If it has the dimensions to be a unitary gate, it will behave like a unitary gate. And if it's doing kind of qubit erasure, then there's no term that will satisfy it. Yeah.
So you had a slide on linearity on this Bang operator you had, and you said that's not a modality, that's a function from type to type.
Yeah.
And I'm just trying to figure out where on this. So are there certain things you can't apply it to, or like, you know, you're showing that Bang AROB is just AROB. Where does this sort of preclude copying?
So it means that like when we're going to apply this rule, we're going to close the nonlinear abstraction. The fact that x of a is on the left context kind of means, like, for instance, like it came from a weakening, and so it doesn't even appear in the term. And so if a, so we have no limit here on the type that can be added. So in a sense, we could add some x of type qubit that doesn't appear in the term. So when we go to close it, the fact that we're performing this, like applying this function to the type, will say that indeed, like, in fact, in the end, this function lambda x t will not be able to be applied to qubits because we'll have erased the superposition in a sense.
I see, and this is the only place the Bang appears in this rule.
in the typing, So it appears here, and it's the only place we use it.
Okay, thank you.
So you showed some type formers that you build unitaries out of if, like branching on ones. Is that the only way you've got to make concrete unitaries, like a particular matrix that I wanted to make?
I think yes. I mean, you can do a lot of complicated syntactical stuff, but I think in terms of like how you would think of a unitary and how you would build it, I think if is the only like direct way of doing it. It's kind of, you think of the matrix and then you just try to write it in these terms. So you kind of think of the columns of the matrix of the unitary you're considering, that those will be the branches, I think.
Yeah. Okay. Thanks.
But then, like, for instance, like the controlled version of this, you can like use Adamar as like a sub part of the term. Could be like if the first qubit is 1, then the rest of the state will be the Hadamard applied to the variable that represents the rest, and you'll use like a let where the true variables have different dimension. I think it works. Yeah.
Okay. Thank you.
Thank you.
Standing by. Okay. Yeah. All right. Next up, we have Mark Koch. He's going to talk about Guppy.
Yeah, thank you, Alex. I want to start this talk going over some, I guess, recent-ish news. Namely, I think 1 month ago, the Unitary Fund came out with the results of their yearly quantum open source software survey, where they asked people all sorts of questions regarding to quantum software. And for programming language people, I think one of the most interesting questions is, which languages do people actually use when they do quantum stuff? And maybe this is not super surprising to you, but as it turns out, Python absolutely dominates this field year over year. In fact, if you're a quantum hardware provider, you're pretty much expected to offer some interface in Python to interact with your device, because this is just what people use. So, like it or not, I think Python is, at least in the near to midterm, here to stay one of the major players in quantum. And I have a small, non-exhaustive list of existing Python frameworks that are out there to do quantum computing. And the current state of play, pretty much across the board, looks roughly like this. Right? I'm sure you've seen this before. We construct some circuit object, and then we call some functions on it to add gates to a circuit. I mentioned there's a few frameworks out there that go a bit beyond that, but I'll get back to those a bit later. You'll notice that this way of going about things is fairly low level. Right? We have languages like Q#, which is at a way higher abstraction level, but in practice, this is what most people are using today. But as many of you know, at some point you run into some issue if you stick to this circuit builder approach. For one example we've been thinking about quite a bit is this repeat until success algorithm pattern that Craig has also already mentioned in his talk this morning. And just to reiterate, the rough idea is we want to apply some operation on a register of qubits, and we do this by allocating some inciders, acting on the register, and then measuring out the inciders. Then we look at the result. If we get some desired outcome, then we're done. We know we've performed the action we wanted to. But if we get some undesired outcome, we have to apply correction, and then we just try the whole thing again. And we keep going and going until we succeed, which is also where this name comes from. Now, the remarkable thing in this algorithm is that we do measurement in the middle of the circuit, which then completely alters the control flow of the remaining program execution. And this offers some fairly interesting challenges related to how do I express something like this, how do I compile it, and how do I optimize it. And in recent years, people have started to get really interested in these things. Just a quick example. This is a paper from last year by Continuum Microsoft, where they looked at how do you compile these sorts of programs at the backend level, and how do you actually run them on actually quantum hardware. But getting back to what I said before, if you wanted to express something like this in this circuit builder pattern, you're going to have a hard time. I'm sure you can come up with some abstractions to express this, but it's not going to be nice or intuitive. Because if I were to explain this algorithm to someone, what they would want to write is a loop, because that's the kind of intuitive representation of these things. And this is where Guppy comes in. What we try to do with Guppy is give people the best of both worlds. What Guppy is, it's a high-level quantum programming language that looks just like Python. Right? So we're targeting people who really like Python and kind of the Pythonic way of programming, but who also want to use some of these more fancy features like mid-circuit measurement, classical control flow, and so on. In fact, since we want people to actually use Guppy, we go one step further and say it doesn't just look like Python, it's actually embedded into Python. So there's a very tight integration between this new Guppy language and what people are already using in Python, which is really convenient because people can just reuse the existing Python workflow if they use external libraries or data processing Python. This all will just work. I want to start by just going over some very quick examples to give you a feel of how programming Guppy feels like. The nice thing about Python is that most people know it, so the syntax should be fairly clear, I hope. But the way you define operations in Guppy is you just write a function that looks like a regular Python function, except you stick this add Guppy iterator on top. So in this example here, we're defining a function that takes one qubit as input and an extra float as input. Then we apply a Hadamard, RZ, and another Hadamard on the qubit, and then we return it. Now, like any other embedded language, Guppy programs are defined in an outer host program, which in our case is a Python script. Right? So we're actually in some example.py file here. And we have this Guppy lang package in Python where we get this decorator from. And the nice thing about being embedded in Python is you can mix and match Guppy code with any old normal Python code. And this opens up some interesting possibilities of making these worlds interact in some way. But I will get back to that a bit later in my talk. One thing you always need in Guppy is a main function, which is the entry point to your program. And in this example, we're just allocating a new qubit. We're calling the function you've just defined, and we measure the result and return it. And once I've defined all my functions I want, I can just call guppy.compile and get my compiled program back. Right? And then I can run it and get some result. At the moment, we're linking this against a quantum simulator, but in the future, you'll be able to actually run this on a quantum device. I'll also point out that this is still a bit work in progress, this execution part, this last line here. I think we have 1 or 2 laptops at the moment that are set up to run Guppy. One of them is in Argentina at the moment, so I can't demo it right now, but we are hard at work to make this run. Also, a very important thing to point out is what this execute thing is not doing is we're not just taking the Python interpreter and we run this code. This is not what's happening. Namely, this program thing we get out is actually a standalone executable that I could save somewhere, I could send it to a friend, execute it at some other time, completely independent of the Python environment. Right? And this also means that the thing that's actually happening when I call compile is we're looking at the source code in the Python file for all functions that are annotated. We parse it into an abstract syntax tree, and then we compile it from scratch. So this means the only thing we're actually inheriting from Python is its syntax. And everything else is completely custom. We can decide whatever we want to do. Right? And in this sense, we try to strike a balance between offering a language that looks and feels like Python, but maybe in some aspects behaves a bit differently, depending on what is most suitable for our quantum domain. In that sense, we're also a bit different from these other frameworks out there that I've mentioned before, so Catalyst by Penny Lane, AutoCASM by Amazon, and Blocks by PLanQC. Because what they're doing is they might do some AST transformations beforehand, but in the end, they rely on tracing the Python interpreter to construct a program representation, whereas Guppy is completely divorced from Python. It's just embedded in the sense that we hijack its syntax. This is a very basic example to show you the true power of Guppy. I've prepared an example from this paper I showed you before that does repeat into success. So what we're trying to do here is apply this single qubit V3 gate on qubit Q using 2 ancillars A and B. Right? And the way we would write this in Guppy is we define a function that takes this qubit Q as input and also a number of attempts we want to try because we don't want this to run forever, right? We want to terminate. And then we just run a for loop, right? Just like you would do it in Python. Then we allocate 2 ancillars in the plus state. And the way this example here works is you can actually split this circuit in 2 parts and first only run the top part. All right, so we can do this like this, and then just measure out qubit A. If we don't get the result we wanted, we can just throw B away and continue, so try the whole thing again. If we succeed, we just implement the bottom part of the circuit, measure the second ancillar B, and if we get the result we wanted, we can break out of the loop, and we're done. And if not, then we apply some correction on Q, and we loop again, and at the end we return. Right, so what this shows is, I think my claim is that this is how, if I were to explain someone what this algorithm does, this is how they would implement it. So I think it's like the most natural way to write it, which is just how Guppy does it. I mentioned that we try to follow Pythonic behavior, but in some senses, Guppy is a bit different than Python, because Python is a fairly unsafe language. What do I mean by that? This code is perfectly fine in Python, but if you were to run it in the case where this B is false, you just get a runtime error because X is not defined. And it would be very annoying if you were to run into such a stupid error on your quantum device where it's been queuing for a few hours. So if you try to pass this code by the Guppy compiler, it will start shouting at you and say, no, if you try to use a variable, you have to make sure that it's actually defined. Right? And similar thing happening here. In Python, it's perfectly fine for a variable to have different types depending on control flow. But in Guppy, again, this is not allowed. If you use a variable, you have to make sure that it has the same type, no matter which path you took to get here. Speaking of types, Guppy is a strongly typed language, like unlike Python, where typing is pretty optional. In Guppy, your programs have to type check, and if they don't, they don't compile. Which is also why in all the examples I showed before, I had these type annotations for inputs and return types, since they're also required to do this checking here. And one nice thing this spices is that we can do linearity. Right? So we can make qubit a linear type, and then catch errors like these where you try to use the qubit twice, or you implicitly discard a qubit here by not assigning the return value. And while these examples are fairly basic, this linearity checking works across any control flow you could write. To write some interesting programs, we also need some data structures. At the moment, in Guppy, we have tuples and lists, but I'm mainly going to focus on lists here, since it's the more interesting case. And also, fair disclaimer, the kind of runtime behavior of lists is still a bit work in progress, so we're hard at work here. Normally in Python, lists look like this, so a sequence of values, and then I can call functions like length on it, which give me the number back. But we could also imagine to have a list of qubits, and since the qubit type is linear, we would also expect lists of qubits to be linear. But in this example here, we would run into some issues, because if you would imagine axis to be a list of qubits, if we actually pass it into this length function, we have a problem, because this consumes the list, and then we couldn't use it afterwards because of linearity. So we actually have a different list interface for linear stuff. We call these linsts, and in this case, you can see the length function actually gives me back the list, so I can use it afterwards. But still, there's some kind of interesting issues with this. Namely, if I were to take this and give it to a Python programmer, chances are they might come up with something like this. So what am I doing here? I have two indices, I and j, and I try to apply a CX gate on my qubit register Qs at this index. Okay? And I'm even writing it back. So this looks innocent enough, but it's actually a big no-go in terms of linearity. Kind of the level 1 problem is to use Qs multiple times on the right-hand side here, right? But even if kind of your compiler is smart enough to understand, okay, I'm actually only using the qubit at this index, it's still not okay, because the compiler would need to prove that I and j are not the same for this to be valid, right? And this is undecidable in general, so not feasible, which points to the kind of broader issue that indexing into lists like this is not a linear thing, which is where I just say, no, you can't do this. Of course, people still want to do these kind of things, like argue with indices, and that's why we add this special higher order apply function that kind of does more the same thing as the line above. But here in the case where I and j are the same, you just get a runtime error. But in terms of linearity, this still works. So that's kind of your way out. If your programmer says, I know what I'm doing, I want to reason with indices, please let me, you can do it on your own risk using this high order function. On the classical side of things, this is still a bit work in progress. At the moment, we only have immutable versions of these lists, because we're still looking at allocation and garbage collection things, but we're hard at work here as well. One thing we can also do is use Pythonic list comprehensions, which are quite neat. In particular, this doesn't only work for lists, but we have arbitrary iterators, or you can do zips or enumerates and so on, which all works. Which is also very nice in the qubit case. For example, here, what this does is just apply a Hadamard to every qubit in my register. Of course, in the linear case, you can't have these if guards, because it would violate linearity of qubits in this case. One thing we want to add in the future is a notion of user-defined types, preferably using Python's class syntax, and then also allow users to define custom methods on these types. One thing I kind of teased at the start is, by virtue of being embedded into Python, we might have some kind of possibility to interoperate, have some compatibility between these layers. And the way this works in Guppy is, let's say I'm in Python and I'm using NarrowX to construct some sort of graph. Then I can actually use this graph in my Guppy function. I want you to focus on this bit here. We have this special pi expression in which you can actually refer back to variables which are defined in your outer Python scope. Right? And the way this works is, at compile time, we're just evaluating this expression and inserting the constant value into the program. And then what we're doing in this example is we're just iterating over the edges in this graph and construct a graph state. Of course, this only works if the type we're inserting is actually compatible with Guppy. Right? You can't just take any old Python class. There needs to be, like, there's restricted sets of types this works with. But in these cases, this works flawlessly. One nice thing this also buys us is interoperability or compatibility with other like classical circuit builder frameworks. For example, what I'm doing here is I'm constructing a PyTicket circuit in the classical kind of builder pattern, and then I can actually use this circuit in my Guppy function by loading it in using this Py thing, and then we get out a function from qubits to qubits that we can call just like any other function in Guppy. And then finally, I want to talk a bit about what's going on behind the scenes, how we actually compile Guppy. Namely, Guppy is compiled to a new intermediate representation called Hugger, which stands for a hierarchical unified graph representation. It's sort of a sister project to Guppy that's developed at Continuum, and it's kind of a new IR for quantum classical programs for optimizing kind of between these domains. So the way we represent graphs in Hugger is as data flow graphs. So the way this works is nodes, boxes represent pure function calls, and then the edges represent data dependency. And then you notice these special boxes here. This is a condition box which executes either of the two paths depending on which thing has been plugged in on top. Right, so this is a structured way of adding control flow to data flow graphs. We have similar constructs to also explain kind of looping and so on. This is also where this hierarchical word comes from, because as you can see, nodes can themselves contain child graphs, and you can nest this arbitrarily deep. Now, if you want to learn more about this, you can head to our GitHub over there and have a look at this spec. Highly recommend it. There's some interesting stuff in there. Once we get this Hugger, we optimize it using version 2 of our new ticket compiler, which tries various things to optimize this. This is also we're hard at work to improve this and offer some good optimizations on these Huggers. And then afterwards, after we have optimized it, we further lower it to some QIR LLVM thing using an MLAR pipeline. But again, this is still a bit work in progress at the moment. Okay, so looking forward, Guppy is on a very active development. We're looking forward to add many new features. For example, we're working on adding more higher level quantum abstractions, things like uncomputation or quantum control. And also things on the classical side, like adding more support for Python's classical types, and also your users to define their own types. We also have some, I guess, more crazier ideas in research directions, maybe adding a sort of qubit reference concept to escape linearity or suspend it temporarily, which we've been thinking about. And then like utility features like adding a language server and debugging. So if you're interested, you can pip install Guppy like this, and you can check us out on GitHub. It's all open source. Thank you.
Thanks. We have time for just one or two quick questions. Somebody? Yep.
So it seems like lists provide a lot of opportunities for violating linearity.
Mm-hmm.
What can you do besides this? I see you can do a list comprehension and put that into a list, subject to restraints. You can do the supply function, but that's saying, hey, we might break linearity. Is there other interesting stuff you can do with these lists?
I guess you can take stuff off them, right? I can kind of uncons or cons them. Take stuff off from the start or the back. But if you try to index into it, that's where problems begin, right?
Mm-hmm.
Other questions?
I was wondering about the deployment on Okay. To real quantum hardware, do you plan to compile it down to QASM or to I didn't know about this QER intermediate representation. Is that executable on quantum hardware?
Yeah, so QER is also the thing that Q# compiles down to, but it's kind of, there are different profiles of what you can do with it. QER is essentially LLVM with like special types and operations that correspond to quantum things, but yeah, it depends on what profile you have, what the device can do, if you can execute it. So that's definitely one pathway. QASM3 is also possible, can also express kind of similar looping things that we're using here, but yeah, we haven't decided yet what the kind of final thing. This is the thing we're pursuing at the moment to get execution working in kind of the medium term, to also link a simulator in and so on. But yeah, many avenues to explore.
Okay, thank you.
Thanks, Mark. Final speaker here. Make yourself known. Oh, it's remote. Okay. Test. Oh, can you hear us, Kinori?
Yes, now I can. Now I can. Thank you.
We can't hear you.
Hi. Can everybody hear me?
Could you share the screen?
Hi. Yeah. Okay. Can everybody see my screen? Hi. Your audio is very
Hi, turn off your camera, please.
Hi. Yes, can you hear me? Hi, can you hear me?
Let me
Hello.
So you said you could hear it. Could you check sound again?
Hi. Hi. Can you hear me? Can you hear me?
Could you try speaking again?
Yes, can you hear me?
Can you continue, just like speak a bit more, like continuously to test audio?
Right. Hi, everybody. I'm Kinnari. I'm a PhD student at ENS Paris-Saclay and Université de Lorraine. Yeah, is that okay?
Okay, that seems to be working. Yeah. Okay, next up we have Kinnari. You might have to speak up a little bit, and we'll have to pipe down because you're a bit soft. But she's going to talk about quantum and classical control, a work in progress. So take it away.
Yes, I hope this is better. I joined the test session yesterday and things were fine, but okay. Before I start talking about my work, I just want to apologize for not being able to make it in person because there were last minute issues with my passport not being delivered on time. Okay, so today I want to talk about quantum and classical control, which is a work in progress and a joint work with a fellow PhD student and my PhD supervisors. And before I begin talking about what we've done, I want to start with a bit of background. Okay, so what do you mean by classical control? Classical control is a principle of design for quantum programming languages where the focus is on interaction between quantum and classical data. Programming languages which are designed using this principle generally support unitary transformations as a fixed set of constants in the language. The upside of using this principle is that you get to model effectful quantum operations like introduction of a quantum state and measurement. Some examples of languages which employ this principle are QPL and the quantum lambda calculus. So what would a very simple typical program look like in such languages? So here it is on my screen. If you see here, this is a conditional statement which either prepares a new qubit or prepares a new qubit and applies the Hadamard gate on it based on the outcome of measuring another qubit. So that's classical control. What do you mean by quantum control? Okay, there are a set of languages which employ this principle, and in this case, the focus is generally on pure state quantum computation. And because of this, measurement is usually not modeled. The priority instead is to be able to provide syntactic support for construction of a large class of unitaries through a custom type system. Some examples of languages which employ this principle are from symmetric pattern matching to quantum control and quantum control in the unitary sphere. You can see the references on my screen. And in such cases, what would unitary look like? Okay, this is a very simple example. It's the C0 gate. The way it's constructed is that you determine the action of the unitary on a certain set of values which kind of cover the type. So the motivation for our work is basically to combine these two things. So what we want is we want a language where you can model interim measurements and build a large class of unitaries. A recent work which aims to achieve this is Qunity. But Qunity is a compilation system in the sense that there's a source level language which is translated to a low level circuit description language. What we do is more abstract than this. So what do? Our language, okay. The way our language works is that there's an entire subsystem which I'm referring to as the quantum control fragment, which is embedded into the main syntax. The way this interaction is modeled in the operational semantics is through something called quantum configurations. And denotationally, the quantum control fragment is interpreted in certain in certain categories of Hilbert spaces. The main syntax is interpreted in certain categories of von Neumann algebras, and there's a functor B which models the interaction. So now coming to the pure quantum subsystem of our language, it has two kinds of types, pure quantum types, the grammar for which you can see on the screen. It's a fairly simple grammar. It supports tensoring and the direct sum. These types are interpreted as Hilbert spaces, where the tensor here in the interpretation is just the tensor of Hilbert spaces, and the direct sum is the direct sum of Hilbert spaces. So in this type system, you'll be able to express the qubit simply as the sum type of the unit type. Additionally, we have something called the QNAT, which is sort of the quantum analog of natural numbers. This type allows for superposition of natural numbers. So something like this, an example would be the state you see on the screen. And we have a second class of types in the subsystem. They're meant to model unitaries. So a unitary from a quantum type Q1 to a quantum type Q2 would be of the type U of Q1, Q2. And these types are interpreted as sets of unitary operators. The syntax of the language looks like this. The key takeaways from this syntax are the parts which are highlighted in red. As you can see, you have two ways of constructing unitaries. One is a more primitive way, and the other is combining already constructed unitaries by tensoring them, taking a direct sum, composition, an adjoint, or the controlled version of the unitary. And amongst the terms, the two interesting terms are application of the unitary to a quantum term and a linear combination of terms which allows you to model superposition. The formation conditions for terms ensure that the linear combination is always a normalized vector, which is important for many reasons that we'll come to later. An example of a unitary in this fragment is C0 here. Other examples with the types are, as you can see here, you have the Hadamard gate, which is a unitary from qubit to qubit. And a slightly more interesting version of the Hadamard gate extended to quantum natural numbers is basically applying the Hadamard gate on 0 and 1 and applying the identity operator on the rest of natural numbers. The semantics for this subsystem are laid down using an equational theory. So, okay, before I go to the semantics, I want to discuss a little bit about the formation of unitaries. Unitaries are constructed using pattern matching. As you can see, the rule on the screen here, there's a predicate OD. It's the orthogonal decomposition predicate, which basically determines an orthonormal basis for each type. And the idea is that to determine an unitary, it's enough to specify its action on the basis. Then the formation rules for other kinds of unitaries are pretty standard, as you can see again. Okay. Coming to the semantics for the pure quantum subsystem, we have an equational theory for terms. So our judgment in this case looks like this, where you say that two terms T1 and T2 of type Q are equal under a typing context gamma. The denotational model is laid down in the category of Hilbert spaces and isometries. So each term is basically an isometry from the interpretation of the typing judgment to the interpretation of the quantum type. And unitaries are unitaries of the type U of Q1, Q2 are basically just unitaries from the interpretation of Q1 to the interpretation of Q2. All of this is tied down in a completeness result, which says that two well-formed closed quantum terms are equal if and only if their interpretation is the same object. Now, coming to the main calculus, it's a standard call by value linear lambda calculus. Its type system is again very simple, but it's augmented with more types to model the interaction with the quantum control fragment. For that, we have NAT, which is the classical natural numbers, and this type B of Q, which is the important type here. It represents quantum data. The syntax for this, for the main calculus is, as you can see on your screen, it's more or less standard, but the important parts are the parts which are highlighted in red. We have the pure constructor, which allows you to introduce a quantum term. We have measurement, as usual, the term for measurement. There's U sub phi of m, which models application of a unitary phi from the quantum control fragment to a term m of type B of Q. And additionally, we have these other two let constructs, which allow you to move back and forth between the tensor in the pure quantum subsystem and the tensor in the main calculus. And amongst the set of values, if you observe, you don't have any closed values of the type B of Q. But this is not a problem because we define something called quantum configurations. And a quantum configuration, here the key thing to note is that the first coordinate of the triple is a term from the pure quantum subsystem. And this also represents the quantum state which is being manipulated by M. And this is okay because the pure quantum subsystem ensures normalization. And you have the linking function, which basically links the quantum part of the term M to the part of the state it represents in T. And although you don't have closed values of type B of Q, we have something called value configurations, which take the form, as you can see on the screen, where bold small v is for quantum values coming from the quantum subsystem. The capital V is for values from the main calculus. The semantics are laid down in a standard small step reduction style, the definition for which is here on your screen. Two important examples are how you deal with the pure constructor. What it does is it basically introduces a state in the quantum term and it reduces to a variable which points to the state. And then there's measurement, which reduces in the standard way. These semantics, they satisfy these nice well-known properties of subject reduction and progress or well-formed configurations. I do not want to tell you a lot about well-formed configurations because they are not really central to this talk. Now I want to motivate some mathematical objects that we use to lay down the denotational semantics for our language. First of all, let's talk a bit about von Neumann algebras. What are they? Okay, they are this nice class of complex vector spaces. To help you visualize what they are, I'll give you two standard examples. One is matrix algebras over complex numbers, and the other is bounded operators on a Hilbert space. The precise definition of a von Neumann algebra is right here, just for brevity. It's right on the screen. Now, this choice is not really ad hoc. It's actually a very popular choice. It's been made in many such works before, and I just want to quickly motivate why von Neumann algebras. Well, for one, you can also, you can combine classical data with quantum data in von Neumann algebras because you can model classical data types. For example, this is a type for bits. Another important aspect is the fact that you can talk about infinite data types using von Neumann algebras. And in terms of giving a more physical intuition, when you talk about bounded operators on Hilbert spaces and the set of NCPU maps between them, they are in a bijective correspondence with CPTP maps on trace class operators on Hilbert spaces. And we know that these CPTP maps, they represent quantum channels in the Schrodinger picture. So you sort of have their equivalence in the Heisenberg picture, which you can talk about using von Neumann algebras. And it doesn't end there. In the event when these von Neumann algebras are commutative, NCPU map between them represents a classical channel. So now I'll go on and describe the categories that we use to lay down our denotational semantics. We use two categories. The first is NMIU. That's an abbreviation. It's the category of Von-Neumann algebras with NMIU maps, which is basically normal, multiplicative, involutive, and unital maps. It's the opposite category. What do I mean by that? The morphisms in the categories are reversed. And the other category that we use is NCPSU, which is again a category of Von-Neumann algebras and normal, completely positive subunital maps. This category is again an opposite category. And both of them are related to each other in a very nice way, which is that NMIU is a full-on objects subcategory of NCPSU. Not only that, NMIU is a closed symmetric monoidal category, which is only true for the opposite and is also necessary for us in order to interpret function types. The other thing that I'm going to sort of reiterate here is this correspondence, because the terms in our language are going to be interpreted as NCPU maps, and this bijective correspondence kind of gives you physical intuition for these interpretations. And another reason why we stick to opposite categories is because they have finite coproducts, which are which we need to interpret some types. Okay, with that, I'll now give you a short description of the denotational model. We interpret types as objects in NMIU and NCPSU. Terms, as I said before, are morphisms in NCPSU. And here on the screen, you can see the denotational interpretation of all the types. And below are the functors and the adjunctions that we use for that. The lollipop here, which is what we use to interpret function types, is the Kleisli exponential, which uses the adjunctions in the figure below. And the bang is an endofunctor on NCPSU. And now I want to talk about the functor B, which basically ties in the pure quantum subsystem with the calculus. It's a functor from the category isometry to NCPSU. It's a strong monoidal functor, and this is why we have those two let constructs in our syntax to basically go back and forth between the two tensors, as you can see here. And what this functor does is it basically embeds the pure quantum subsystem into the main calculus, as is obvious from the interpretation of the type B of Q. B of Q is just the interpretation of Q, which is a Hilbert space. And on that, you apply the functor B, which gives you a Von-Neumann algebra. The introduction and kind of elimination rules for this type are the pure constructor, which introduces types of the form B of Q, and you have the measurement term, which returns something of type Q bar, which is a classical type, and it's defined through an inductive translation on pure quantum types Q. And so that gives you a picture of how the denotational model works. And now to conclude, we have certain results which are a work in progress. We have the small step soundedness. Here, the small PR CC prime is just the small step reduction probability from the quantum configuration C to the quantum configuration C prime. We have big step soundedness, where now capital PR is the big step probability of reducing to a value configuration V from a quantum configuration C. And finally, adequacy, which is a corollary. And here, halt of C is just the probability of termination when you start with a quantum configuration C. Okay, and to conclude the talk, I just want to talk about some future work, which is just that we can add support for more general inductive types in the language. And another more important aspect is to add support for lambda abstractions which manipulate unitaries. And finally, just to drive through what the work does, I give you a quick summary of what we do. We have a language which combines interim measurements with syntactic support for constructing a large class of unitaries. We have a very physically intuitive denotational semantics, a clear operational semantics, which is defined through an adaptation of quantum configurations. And the most important aspect of this is to come up with a language which is more higher order and allows you to write something more abstract and hence move away from circuits. Okay, so that's my talk, and now I'm open for questions. I hope you were able to make most of my talk. Yeah.
Okay, thank you.
Yeah.
Are there some questions? Yep.
Hi, this is just a minor point, I think, but I see that in your type system you can make Hilbert spaces of the same dimension in different ways. And I wondered if
Yes.
that matters in any programs that you might write.
So we do prove that both the ways are equivalent, and beyond that, I think it's just a matter of choice, I'd say. Yeah.
Okay, thanks.
Yeah.
Other questions? Yeah, I have a question. Could you go back to the slide on the denotational semantics?
Yeah.
Yeah, that one. So on the, I'm interested in the arrow type. So
Mhm.
where you have the lollipop outside of the brackets, is that taking all the MIU or the in MIU maps between those two von Neumann algebras? Is that how I should read that?
Yes, yes.
And that thing's a von Neumann algebra.
Yes.
Okay. And this is why you need these kind of the separation between the CP category and
Yes,
the MIU.
yes. It's exactly, yeah. We need the LMIU category exactly for the Kleisli exponential, because it's close symmetric, but NCPSU is not, and you need the close symmetricness to sort of curry for currying, yeah.
Okay. Other questions? Okay, let's thank Kinnari again. Thanks.
Okay.
Thank you.
Thank you.
the fourth and final session of Planck, and indeed of the entire POPL combined conference. Our first talk of the session, shuffled around slightly, is going to be Anirudh Piduri talking about quantum correctness by construction. So Anirudh, feel free to take it away.
Yep, thank you. Can you hear me fine now?
Yep.
Okay. Yeah, thanks, Robert, and thanks to the organizers and the AV team for putting together this remote talk. That was really nice. Yeah, so I'll be talking about joint work with Ina and my supervisor, Michael, at Bochum. So why do we need to, maybe to start with motivation, like why do we need to verify programs? Like as programs become larger and larger, there's higher chance of them containing mistakes and bugs, and we want to be able to catch them without having to run into them when execution. So yeah, there have been a lot of different approaches to verifying programs. Like there have been logic-based approaches and more rigorous things like unit testing, where people just write different tests and you can check programs. But unfortunately, for quantum algorithms, we do have a few challenges that we don't have in classical programming. The first is there's generally a lack of hardware to run larger quantum algorithms, so you can't really use strategies like unit testing. And even if you could, there is an issue of measurements collapsing the state, so you can't really inspect values the same way you would when debugging classical programs. So you somehow need a more formal way of reasoning about quantum programs to actually check that they're correct without having to run them and inspect like intermediate values. So like a very standard way of doing this is using Hoare logic, where you specify the correctness of a program by giving a precondition and a postcondition. And what this means is for any input state that satisfies a precondition, if you run the program on that, the output state will satisfy the corresponding postcondition for the program. And there are two main philosophies or ways of approaching such a verification, approaching verification in this model. The more standard one that most people are familiar with is post-hoc verification, which was pioneered by Hoare and a lot of later work to that, where you start with a program that you're interested in proving and you have a specification that you want to prove that the program satisfies, and you go about reasoning on that. So this is a standard bottom-up approach where you try to prove things about each statement in the program and combine them to put together a proof for the entire program. But unfortunately, this usually requires you to have the whole program beforehand so that you can actually reason about it bottom up. And there is a nice, interesting alternative way to do this called correctness by construction, which was pioneered by Dijkstra in 1975, and a lot of later work following that, where you instead start with just the specification that you're interested in, that you expect your program to satisfy, and you build your program step by step with a top-down approach where you try to discover like program details on the fly. But at each step of filling in the program and writing something like a slightly larger program, you make sure that this step is indeed preserves correctness of your program. So at the end, you will end up with a full program and it is guaranteed to be correct. So how do we do this for quantum? Like first we consider an extension of classical logic for quantum, which we follow the formalism of Ying, where you have quantum predicates, which are just measurements P, and if you measure with a density matrix, a state rho with this measurement P, the outcome is, the expectation of this is given by trace P rho. And for an arbitrary quantum program, we denote by brackets S the denotational semantics of this, which corresponds to the function that transforms input density matrices to output density matrices. And we say that a corresponding quantum Hoare triple P SQ is correct if the probability of the postcondition holding in the output state is at least the probability of the precondition holding in the input state. So this is somehow a generalization of the truthness not getting lost. So everything that was indeed correct before stays correct, but like there could be other states that could also satisfy the post condition, and you're okay with that. So we take a simple quantum programming language which has all standard instructions that you would have in a quantum circuit, but it also has control flow based on classical measurement outcomes in this if and while construct. And this while is this repeat until success paradigm that was described in an earlier talk. So you repeatedly measure with this binary measurement B on a set of registers Q, and if the output is 1, you keep repeating the program body S. And in our work, we extend this language with an extra construct called a whole, or in this case, a typed whole, which has this context PQ, that is the corresponding predicates that you want the final program to satisfy. So in the end, we will fill in this hole with a program that contains no holes. And the way we fill it in will guarantee that the whole triple PSQ will be true at the end. So how do we do this? We have a sequence of we have a set of refinement rules. Each refinement rule tells you that you can replace a particular whole PQ with another program S, which could possibly contain holes, as long as the set of conditions that accompany it are satisfied. And the nice thing about this is once you fill in a hole with a concrete with a different program, you can completely forget about the initial specification PQ and only worry about the remaining holes in the program that you need to continue filling in. So maybe a few examples of how these refinement rules look like. One is you can just fill it in with just initializing a quantum register as long as you check this matrix inequality on the right is true. And here A less than B is just in the Loeffner order over positive different matrices. Or you can even apply just a single step where you apply unitary by checking this constraint, or something slightly more non-trivial. If you want to refine to a sequence of 2 programs, then you can just pick any arbitrary intermediate condition and you just get 2 holes. And you can now successfully independently refine each, like the left and the right hole, which is PR and RQ. And some things, an extension of the sequence, if you want to repeat a program a finite number of times, then you just need to find a sequence of predicates R0 up till Rn that satisfy this constraint. And the body has to basically satisfy Rj to Rj plus 1 for every j from 0 to n minus 1. So later on, when you fill in the body of the program, you just need to check this constraint for each of the preconditions Rj and postconditions Rj plus 1. So now, like a non-trivial, like all the constructs that we have described before are somehow things that you can unroll into like a finite depth quantum circuit, which is not fully like general. So with while loops, we get something that you can't really unroll anymore. And for this, we have a slightly more non-trivial rule, which says that you can refine it to a loop, and the body is so such that like you find a sequence of sequence of predicates R0, R1 up to like for every natural number Rn, which converge to a limit R, and the limit has to satisfy a certain constraint on the precondition. And if you look at the body essentially states that the intuition is that Rn here captures all the states that exit the loop after running for at most n iterations. So now if we read the body, it says that if you have a state that would take n plus 1 iterations, then after running the loop body once and measuring, then either it exits the loop because you get an outcome 0 and the post condition is true, or it stays in the loop, but this Rn is true, which means it can only run for at most n more iterations after this. And this is like a generally correct while rule that we have in our refinement system. And in the paper, we prove that the refinement system that we provide is both sound and complete. That is, if you here arrow star means that you've applied a refinement 0 or more times. So that is, it is sound. That is, any program that you construct finally that contains no holes will have to satisfy the corresponding whole triple that you started with. And any valid program that you have that you know satisfies the condition, there is always a sequence of refinements that you can use to construct this program. So now like I'll just try to illustrate this refinement philosophy by just using a simple example to construct an algorithm for quantum search. The search problem, as everyone knows, we have a function that takes n-bit strings and produces a binary output, and we want to find one input such that the output f of x is 1, and we call these solutions. And for example, in this example of function f, there are two valid solutions, and we'll now construct a search algorithm in the variant where we assume we know the value of t, but we need to find a solution for the function f. So how do we do this? First, the input f is given usually as an oracle that computes the value of f, or we can always transform this equivalently into a phase oracle that just flips the phase of the input register. And how do we specify that a program is a valid search algorithm? I claim that if I use the precondition pi and the post condition as the sum over all solution bit strings x, the projection on x, then this is a valid specification that says that this algorithm does search and succeeds with probability p. Why is this true? If you plug this back into the definition of correctness, it just simplifies to p less than equal to this value, which is just the probability of, if you measure the output state in the standard basis and take the probability of obtaining a solution bit string, and that is at least p, so which is the success probability of the algorithm. So now we'll basically refine this corresponding specification in 4 consecutive steps, each step by applying one idea after the other. The first thing is we instead of starting from a random input state, we initialize it to the uniform superposition of all bit strings, and this is somehow equivalent to like classically sampling a random bit string if you just stop the program at that point. So how do we do this? We just use a sequence of refinements, and you can set q to 0 and apply the Hadamard gate on all the qubits. And if we plug this back into the requirement for these two instructions, we get that p has to be at least this inner product u r u. And because we want to maximize the success probability, we just choose p to be equal to this value. And now we have the second part of the program, which starts with this state and needs to produce a solution. And the second step is I can slightly make my life harder by saying, okay, like I don't want just something that measures and gives me a solution, but I want it to give me a solution with equal, like any one solution out of these t with equal probability. That is, I want to build this good state, which is a superposition of all the solution bit strings. And this is naturally a harder version of instead of just producing a solution. And so this we can check the condition for this is trivially satisfied. So now, yeah, we start with the uniform state and we want to reach the good state at the end. So the idea of Grover search is that, okay, like because this uniform state U and good state ket G lie in a 2D subspace, we can effectively rotate from one to the other and get as close to G as possible. So how do we do this? We can write down this 2D subspace with the other orthogonal basis vector, which is ket B, which is the superposition over all non-solution bit strings. And any arbitrary state in the subspace can be parameterized by a single angle theta as cos theta ket B plus sin theta ket G. So the good state is now just at an angle of pi over 2 from the state ket B. And the uniform state is at an angle alpha, which is sine inverse of square root t over n, which can be checked from the initial definition. And we choose our success probability p to be this, which we will try to maximize as we construct the program. So how do we do this? We can, to be able to rotate from the starting state to the good state, we can try to find some rotation that makes some progress and then repeat it enough times that it gets as close to ket G as possible. So we can say if I can find a rotation delta, then I can repeat it enough times, r times in this case. So this delta is something that I'm going to try to figure out later on. But for now, if I have a rotation by delta, then if I repeat it r times, then I want this r delta to be close to pi by 2 as possible. That is the success probability p. The expression simplifies to just sine square alpha plus r delta, and I want this to be as close to 1 as possible. So once we have a value of delta, we can just pick r that satisfies, like maximizes this value of p. And we can simplify this loop body by just saying instead of only having to rotate by delta for these particular input states, it has to work for every state, which is just a harder constraint. And so naturally, we can always ask for a harder problem to solve. So now we just need to find the loop body that starts from ket theta and goes to ket theta plus delta for some choice of delta. So, and first we notice that, okay, the only unitary that we have that gives us access to the input is this a phase oracle PF, and that indeed is a reflection about the state ket B. So if I do that as my first step, then as long as I'm able to find another reflection, I can effectively get a rotation. So after doing this, the intermediate condition becomes state ket minus theta. And now I just need to find another reflection about any known vector that is independent of the problem. So here I just pick the state ket u and reflect about that. So, and because this reflection takes an angle of, is about an angle of delta by 2, then, and the actual reflection I perform is about alpha, we just get delta equals to alpha. So we just plug this back into our definition for P, which gives us the success probability of sine squared 2r plus 1 times alpha. And this is maximized if you pick r close to approximately pi over 4 times square root n over t, like with the small angle approximation. And if I write down the entire program that we have, that we refined step by step, this is the thing we get, which is basically Grover's search that we were able to construct one step at a time. So, like in general, this gives us a nice framework which you can use to successfully refine and build correct quantum programs. And at each step, you can decide what key thing you want to focus on and what you want to refine, like by using information that you already have. You can also easily extend the system by adding more complex rules that are a composition of existing rules that one can directly use as corollaries in later constructions. And yeah, the paper is on arXiv, and some of the new additions about proof of completeness will be updated soon. Thank you.
Thank you. So we have time for questions. Okay, while people think of their questions, I will start with some of mine because I have a bunch. Ordinary Hoare logic is, you know, you often just have to figure out the invariance, and you can kind of mechanically, you know, go backwards through the program, applying the assignment rules and so forth. And I think that's possible in Ming-Cheng Ying's logic as well. Is there a sense in which you can kind of naively, given the specification, fill in the blanks in this logic?
Yeah, like it's not full. Like for instance, if you consider the while rule, which is the most difficult one, it's not entirely clear how to compute these invariants are. And if you had the program, then Ming-Cheng's work has some way of computing these bounded functions, which are based on the actual program that you have. So it's not fairly like straightforward that you can compute it. And I think in general, if you have a very large program and you just know the specification that you want the whole program to satisfy, it's really not clear what you want each sub-step in your program to satisfy. If it's just one or two things, then you can maybe reverse engineer and figure it out. So I think the idea of QBC is that it gives you a natural way to do forward reasoning where you try to figure out like, okay, if I want my whole program to satisfy something, what should the subparts of it satisfy? And then you can combine it with a standard post hoc approach to like somehow meet in the middle and like verify large programs.
Neat. Other questions? Okay, so I had one more thing that I was just wondering, which was, were there any like programs that you found were particularly amenable to this kind of construction? So in other words, specifying first kind of what you were trying to do made it easier to write the program itself?
Not really, but I did like the fact that for Grover's search, like writing the specification is fairly straightforward. But figuring out I guess because people know this really well, they kind of know the exact specification that each substep should satisfy. But here we were able to actually push it through and get that, okay, the loop body should satisfy this recurrence that you have to jump by an angle of delta each time. So like it's nice that you just start with just a simple specification which makes intuitive sense, and then you can reason about like subparts of the program like forward.
Makes sense. Okay, so we have another question.
So it's something of a variant on the previous question. So one of the ways that correctness by construction is often realized is by attaching invariance to types and to data structures. So of course there are no data structures for the moment in quantum computing, but do you think that this could, do you have any idea of what it could look like if we had data structures, or what kind of data structures would be useful to attach the kind of invariance that you need at the moment?
That's a good question. We did not really think of any more complex data structures other than just simple quantum registers. And yeah, I guess like back to the question of this variance and invariance, yeah, like if you refine to a loop, okay, here I just stated simply that you just need to find the sequence R naught up till infinity, but usually you would find these as more structured like predicates based on like maybe as a combination of a loop invariant that you expect to hold and a variant that is somehow increasing till the limit so that the program actually eventually terminates. So yeah, there's some interesting things to consider in giving a more structured way of constructing these invariants instead of just saying, okay, like these are, like you just need to find an arbitrary sequence that might or might not make intuitive sense. But yeah, like in terms of data structures, I don't have any thoughts.
Thanks.
Okay, thank you, Anirudh. So our next talk will be by Gabrielle.
Independently. They can synchronize with some communication primitives, and we often have non-deterministic behavior, and since we're doing quantum computing, also probabilistic behavior resulting from measurements. To model such quantum protocols, we resort to quantum process calculi. So our processes are terms of an algebra, and the operators of our algebra are the ways of composing together processes just corresponding to the features we've seen before. And to give the semantics to these process algebras, we use label transition systems. So a set of states with a transition relation. For example, here we're talking about quantum process calculi. We use transition systems where the states have this form. So a pair with rho, a density operator representing the quantum values, and P, which is a process that is the classical part, similar to what is done for the operational semantics of imperative languages. Here we can see, for example, the semantics of a parallel composition. We have a process on the left, a process on the right, and they can execute before left then right, or right and left non-deterministically. For an example of quantum behavior, we see that suppose we have starting on the phi plus state, so a 2-qubit entangled state. We perform a destructive measurement on the first qubit in the 0-1 basis. And we see that after a transition labeled as tau, we end up in a probability distribution. Probability distribution of the configuration where we are left with the 0 state or the 1 state. So this is a probabilistic LTS or PLTS. When working with PLTS, the notion of semantic equivalence of choice to compare their behavior is bisimilarity. Simply put, two LTS are bisimilar if each one can replicate, can emulate the behavior of the other. So to make an example, similar to the one before, phi plus gets measured in the 0-1 basis, measured destructively, or get measured in the Hadamard plus-minus basis. Should these two transition system, probabilistic transition system, be bisimilar? For the most proposals in literature, they are not. Because generally the process on the left goes with a 1 alpha probability here, when we can see the 0 state, and the process on the right cannot replicate this behavior because ket plus, ket bar plus is observably different than ket bar minus. But if we think about it from the physics point of view, what we have here in these distributions is just a mixed state. And we know that representing them as mixed state, a mixture of 0 and 1 is identical to I over 2, that is identical to a mixture of 1 and 2. So our argument is that the natural notion of probabilistic bisimilarities on such probabilistic transition systems of quantum configurations is not adequate to model the observational capabilities and observational limitations of quantum theory. We already tackled this problem in our talk at POPL a few days ago. We proposed constraint-saturated bisimilarity, which keeps this model, so probabilistic transition systems, and changes the notion of bisimilarity. But it also has some disadvantages. First of all, our proposed bisimilarity is not a congruent, so it's not preserved by the operators of our process algebra, and we lack algorithmic verification because, in general, if we're given, for example, a process and its implementation, to verify that they are equivalent, that they are bisimilar, we should build an infinite number of transition systems, one for each possible quantum input, and verify that they are bisimilar. So we try a different, more foundational approach. We want to represent them in a new semantic model, and we want, in particular, to represent the correct observational properties of quantum systems. So, go back to physics. How to model the observable properties of quantum system? Through FX. If you're not familiar with them, FX are parameterized probabilities. That is, they are convex functions that when you give them as input a quantum state, they give you a probability. In a sense, they are fuzzy predicates on the set of quantum states. But at the same time, these functions can be represented neatly as matrices, as d by d matrices, smaller than the identity positive matrices. So we will continuously go back and forth between fx as matrices and fx as function on states. And this homomorphism is just the well-known Born rule of taking a state and multiplying it by this effect, so this measurement operator if you want, and taking the trace. This is from what we start, and we will build increasing structure on these effects. From fx we can build effect distributions, so functions that to assign to each state of a carrier set x a weight that is an effect. We require that the support of a effect distribution D is finite, so the set of x that have some weight, some non-zero weight is finite, and the sum of all these weights must be smaller than the identity in the loner order. If you reflect upon this, this is a generalization of usual probability distribution. These are just probability distribution are one-dimensional effect distribution because 1 times 1 matrices are just real numbers. But since effects are parameterized probabilities, effect distributions are parameterized probability distribution. We have exactly the same lifting, the same isomorphism as before. We can lift it in a pointwise manner. So on these new effect distributions, we can perform some operators. So we have the point distribution or delta distribution. We have weighted sum of distributions in which we have as weight effects in general and not just probabilities. Notice that here we are composing effects and distributions with the tensor operator. So in our intuition, this represents that we are building a bigger effect that is measuring more qubits. So this operation here represents some kind of measurements where we first measure the first qubits, and if we get this outcome I, then we'll continue measuring the distribution defined as the I. Then, as with the probabilities, we can lift a relation on states to a relation on probability on effect distributions. So we say that two distributions are related when two states are related, then the point distributions are related. And if we have n distributions that are related, their effect composition is still related. Thanks to effect distributions, we build effect transition system. Again, a generalization of PLTS. An LTS, we have is a set of states, some actions, and a transition relation that from a state and an action goes in one or in possible many effect distributions. Here we can see that we have effects as weights on this distribution. We can have also sub-distributions in general, and we can still have non-deterministic behavior. What can we do with these LTS? Our idea is that we will use them to model quantum protocols. So we are interested in representing in this semantics object those features of programming of quantum protocols. So we have non-deterministic sum of LTS. We have parallel composition of LTS with also synchronization. And we have evaluation of an LTS, because an LTS, again, is in a sense a parameterized probabilistic LTS. From this LTS here, where we have effects as weight, we can instantiate it with a state rho and get a probabilistic LTS. It's exactly the same structure as before, but on the weights, instead of having an effect like d of s prime, we have a probability that is just applying the Born rule. So we have trace of d of s prime times rho. If rho is bigger, then we can take the partial trace. But interestingly, for this kind of LTS, we can define two different notions of bisimilarity. The first one is the Axel-Mendel bisimulation, and Axel-Mendel bisimilarity simply says that when S and T are bisimilar, it's required that when S goes in a distribution delta, then T can replicate the behavior going in a distribution theta, and delta and theta must be related by that relation lifting we see before. Otherwise, Larsen-Scope bisimilarity requires that S goes in delta and T goes in theta, but delta and theta must essentially assign the same weight to the equivalence classes of R. So we are requiring that R is an equivalence. These two notions, interestingly, give exactly the same, these two definitions give exactly the same notion of bisimilarity for the probabilistic case. They are both called Larsen-Scope bisimilarity usually, but in the quantum case, we have two different relations. To see an example, here we have 0 and 1 as weights of this effect distribution, or either just I, that is a complete effect distribution, or plus and minus. When we're using Axel-Mendel bisimilarity, these are not bisimilar because we have the same pattern as before. Tau cannot replicate the behavior of S because S goes with a Kepler 0 weight, and Tau can only go with a Kepler plus and Kepler minus weight. But if we instead are using Larsen-Scope bisimilarity, they are bisimilar because we are considering the equivalence classes. We say that S1 and S2 are equivalent because they are in deadlock, as well as V, as well as T1 and T2. So we say that S goes in this equivalence class of S1, S2, with a weight that is the sum, that is category 0 plus category 1. That is exactly the identity, that is exactly the weight of category plus plus category minus. So we have that Axel-Mendel bisimilarity is strictly coarser than the Larsen-Scope one, and we advocate that this Larsen-Scope bisimilarity is the notion of choice for ELTS, because we can resort back to the probabilistic behavior we've seen before. We have this operation of instantiating, of evaluating an LTS, and we can prove that if S and T are bisimilar, then for any possible input, when I instantiate them to probabilistic LTS, these probabilistic LTS are bisimilar. Then we can finally use our effect transition system to give you the semantics of quantum protocols. We start from a very minimal example because we are interested in understanding how the most basic features of quantum entanglement and measurements plays along together with non-determinism. So we just have communication, we have non-deterministic behavior, parallel composition, and measurements. We only talk about destructive measurements. For this kind of process algebra, we can give a novel effect semantics, a sort of Heisenberg-style semantics. It's different from what is done usually, where we have a state, the quantum state, and we update it as long as we continue. Here, instead, we do not represent the quantum state, but we update the effect after each transition. We update the set of effects that we would apply on a state. So let's make an example. Here we have, starting from the unit effect, we have a process that performs a tau transition and then a measurement. If I measure 0, I continue as P. If I measure 1, I continue as Q. And so it gives us, of course, an effect transition system with these weights. And we store inside these configurations, where we have an effect and a process, we store the effect we've just seen. Because if we, for example, suppose that P now performs plus-minus measurement in the Hadamard base, we accumulate these effects on the weights and in the configuration. So a tau move, and then we see the weights 0 plus and 0 minus. Why we do this? Why don't we leave just 0, 1 here and plus and minus there? Because we are interested in, of course, dealing with entanglement. And if we have entanglement, we have just we have to consider the composition of effects to, for example, notice the differences between phi plus and phi minus. If we just have if we just had effects one after the other, we couldn't catch these differences in the phase. So, going to conclude, we have this new Heisenberg approach where we have configurations with effects and process. We can give the usual Schrödinger approach with a transition system with states and processes. And interestingly, they are the same in the sense that if we take this effect transition system on the left and we evaluate with an input rho, for example, here with the 0, 0 state, we get exactly this probabilistic transition system. This is for our small language without unitaries, but we can add unitaries as well. We simply, instead of configurations with effects, we must also store super operators in general to keep track of the effects of unitaries on states. But the structure, the algebraic structure, is the same. It is still an ELTS with effects on the labels that when we measure, when we apply an input state, gives us a probabilistic transition system. So this is our main theorem. Our effect semantics is correct and complete with respect to the state-based semantics. This means that two states are bisimilar in the Heisenbergish approach if and only if they are bisimilar when we plug the state inside it. And this means that instead of building an infinite number of probabilistic LTS here to compare if two protocols, if two processes in general are bisimilar, we compare just one couple of effect LTS, allowing for algorithmic verification. So this is the situation we have now. We have improved. We now also have the possibility for algorithm verification. We have quantum indistinguishability because we are using exactly what quantum theory prescribed as observational properties, and we are still investigating, it's a work in progress, if our notion is a congruence for our operators and if it maintains the correct notion of non-determinism. That's it. Thank you.
Thank you, Gabriel. Questions?
So I was a little bit confused. So which actions are observable if I have a different measurement? Your motivating example is I'm doing a different measurement, I'm arriving at the same mixed states.
Yeah.
But then the choice of measurement isn't observable in the system? What's going on?
Yeah, because, for example, also here, we predicated that we should not observe the difference of measuring the 0, 1, or plus and minus base if you do not communicate the action as before. So in this case, since these states are all bisimilar, if a faraway party measures in the 0, 1 or plus minus basis without telling you anything, you should not be capable of observing anything, even if you have entangled states with them. So we just, otherwise, if we had different classical behaviors here between S1, S2, in that case, we of course observe that this branch here has a 0 weight and this branch here has a plus weight. There are some observable differences.
Okay. No, it's I didn't realize that you intended the choice of measurement to be a private action.
Yeah. That's the idea. In a protocol setting, we don't know what the other processes are doing. Yeah.
Other questions? So I was wondering something. When you had this AM similarity,
yeah.
It looked like it was insufficient in part just because kind of you could get to two distributions that should have been equivalent but were not identical. Could you kind of extend AM by similarity
yeah.
by taking like a closure of this? In other words, if it takes you to two bisimilar in a sense.
And then we can apply some equivalence on these bisimilarity, on these distributions. This is actually, thank you for the interesting question. This is an approach we tried a few times ago, but is less natural, I would say, because, for example, it becomes difficult to have a bisimilarity that is closed for composition, that is transitive, because if, for example, okay, S goes here and T goes there, and they are not bisimilar, but I can rewrite them to be bisimilar, it's fine. But then if I have something else, for example, X that goes in YZ, then I don't know if my rewriting here is the same that goes from T to X. So it risks to break the transitivity of our bisimilarity that we need.
I see. Interesting.
Yeah.
All right. Thank you very much.
Thank you.
Right, my name is Kengo Hirata, and I'm going to talk about quantum if statement as in the former talk. But what we're going to talk about is quite different thing, and which you might think weird. And this is a. Oh, so sorry. And this is a joint work with Takeshi Tsukada. Right? Oops. So in this talk, we're going to talk about a program which looks like this. And in this program, you see measurement and quantum myth. But there's an obvious problem that measurement appearing inside a quantum myth, which means that if you try to write down in a circuit, you get a program which looks like this. This is quite weird. But we're interested in this kind of program. Why? Because we have a motivating example which has something look like this, which is called quantum switch. So quantum switch is a quantum channel made up of two quantum channels, E and F, and it applies EF or FE under the control of a qubit X. But there's a problem that in most of the programming language, we cannot write this quantum switch. It's because most of the programming language refuse to write measurement inside quantum myth. We can only write uniters inside this quantum myth. So you might there might be several explanations we have to have this kind of restriction. But technically speaking, from the point of view of semantics, we can say like, this is because the semantics for quantum control channel is ill-defined in general. Well, but there's a quantum programming language called QGCL, which has quantum myth and measurement without limitation of measurement appearing inside quantum myth. Yes, this is pretty nice, and Yang had defined the semantics, but there's some remaining issues. The first issue is that in that semantics, we cannot know how to implement program into a circuit. And the second issue is that there's some ambiguities in the semantics. It means that there's a parameter in the semantics, and if you choose a different parameter, you get a different semantics. So the question we want to address in this talk is, can we define a clearer semantics with simple physical implementation for such kind of programs? So what we're gonna do is to think about a language which is essentially the same as QGCL, but we're gonna give a different semantics with different approach, and think about different semantics. Right. So what we're gonna propose in this talk is a program transformation technique. And in this program transformation, given a program which has measurement inside quantum myth, we're gonna transform it to a program without such kind of measurement. And the key idea we're gonna use in this transformation is to defer the measurement from the inside of quantum myth to the outside. And as a result, we're gonna explain that with this semantics tells that we can have an obvious physical implementation to a quantum circuit. And we want to explain that as an application, we can use this technique to give a semantics for a program which is something called like quantum controlled while loop. Right, so let me talk about the program transformation algorithm first. The language we want to consider has only two types, and which is quite simple. The one is the qubit, and the other is Boolean. And we have to use this qubit in linearly. And the example we want to consider is looks like this. And so this example, the idea of the example is just a quantum control measurement. But this program has a little bit problem. I mean, the outcome of the measurement has to be Boolean, but this P is qubit, so I just fix this type error, and we get a program like this. So what we're gonna do is to transform this program into a program without measurement appearing inside a quantum myth. So the algorithm we're gonna consider it consists of 4 steps, and the first one and second ones we're calling differing measurement. And the difference is that the first one only touches the program which is inside a quantum myth, And in the second step, we're going to move this measurement to the outside. In the third step, it's something we are calling introduction of dummy value, which makes our semantics also ambiguous. And the last step is not interesting step. I'm just gonna change the appearance of program for simplicity. So let me now move on to the first step. So first step, we changes a program which is only inside the quantum if. So given a program on the left, we have measurement at the top of this block, and we're gonna change it to a program which measurements appears in the bottom. And the algorithm we use here is a classically known one. It means that writing this in a circuit, we're gonna transform a circuit on the left to the right, which is known to be equivalent in semantics. And in the second step, we want to move this measurement to the outside, but we don't know how to do that, but we just forced to move to the outside. So this is so simple. And writing this in a diagram, we given a program which on the left to the program on the right, just moving the measurement to the outside. Yes, so this step is so simple, I mean too simple, and which causes some problems. The problem is the type mismatch. So looking carefully this program, P0 in the then clause is not consumed because it's only used as a conditional of a quantum if. But looking in the else clause, P0 is renamed to P1, which means that P0 is already consumed after applying this else clause, which means that P0 is used differently in the then clause and else clause, which is a problem. So looking at the else clause, after running this else clause, we have to use P0 again, which means that we want to use P0 twice. So what we're gonna do in the third step is to fix this problem by redefining P0 just after the first use. So what we're gonna do is to insert the program on the right, which means that redefine P0 with a dummy value. What I'm calling a dummy value is an arbitral quantum state. So we're gonna choose a arbitral quantum state and insert the red colored line. So I mean, if we choose cat0, we get a program which on the right, and if you choose cat plus, we get a program on the right. And after applying the third step, we get a program which looks like this: control isometry followed by measurement. And in this final step, we just change the appearance to a simple looking one. I mean, a definition of initial states followed by controlled unitary followed by measurements. So this is not interesting. So let me summarize our algorithm. We first move the measurement in the then clause or else clause to the back. And in the second step, we force to move to the outside of quantum if. And in the third step, we fix the problem which is caused by the second step, which means that the violation of linearity. And finally, we change the looking to a simple looking one. And so this whole algorithm is quite simple, and the resulting program has a obvious implementation into quantum circuit, which means that applying this algorithm, we get a quantum circuit, and so we get we know how to compile a program into a circuit. Right. So we did a little bit weird thing. So what we get as a semantics. First of all, this algorithm works well with quantum switch, which means that our semantics by this transformation technique defines the correct semantics on quantum switch. That's good. And secondly, we compared our semantics with Yang's original one. So let me review the semantics defined by Yang. So he defined two semantics. First one is the original one, and the second one is a kind of generalized semantics, which uses some parameters, and if you choose a different parameter, you get a different semantics. And what we have observed is that, at least in the simple example we have explained, the choice of parameter in QGCL semantics is exactly the same as our introduction of dummy value. And we can give a different explanation for this parameter. I mean, we had to introduce this parameter for for a pure type theoretical reason, and which is a new point of view. We also compared our technique with Abel et al.'s observation. So Abel et al. Observed that to define a quantum control channel, we need not only the class of the composition of channels, but we also need the kind of more additional information of what they call initial state of environment. And what we have observed is that this initial state of environment is quite closely related to our dummy value, which means that we could found a non-trivial connection between Yang's semantics and what Abel has observed. So finally, let me explain how can we apply our technique to the semantics of quantum control while loop. So quantum control while loop, it's a program which looks like this. So we have we have 2 qubits and a quantum while controlled by a qubit. And M is a program which updates the D and Q. So we already have several semantics, several work about this semantics. And first of all, Badescu et al. Has observed that in their domain theoretical framework, they could not give a good semantics for this kind of program. But there are other work that's Yang et al., done by Yang et al. And Savary et al., and both of them could define the semantics of this kind of program using infinite dimensional Hilbert spaces. And the difference is that with the semantics defined by Yang et al., we cannot know how to implement this program but Savary et al. Observed that they can know how to compile this program with using a list of qubits. So we want to focus on the work done by Savary et al., which has implementation, but they had a limitation that in the program M, which updates inside the quantum while, has to be unitary. And the question we want to address is this. Can we remove this limitation of M to be unitary by applying our technique and move the measurement to the outside? Yes, why not? So what we want to do now is to transform a program which has a quantum while with measurement into a language defined by Savary et al. So Savary et al. Use a language which has quantum control recursion and list of qubits. So the algorithms. So let me move on to the algorithm. The source program is quantum while. And in the first step, we applied our technique to this M. So applying our technique, we get a program which consists of 3 parts. The definition of initial states, followed by unitary part, and followed by measurement. So what we can learn from this program transformation is that we get a program M bar, which we can consider it as a unitary part of this program. And so we want to translate this quantum while into a language defined by Savary et al. And the key idea is to prepare the list of these Q's and A's and apply this M bar at the ith iteration, so M bar to Qi and Ai in the ith iteration. And and we also want to move this measurement to the outside of quantum while. So this is the translated program, which consists of 2 parts. And the first part is the definition of a recursive quantum while loop, recursive quantum program, which is a helper function. And the second part is how to run this program. So we prepared the list of Qs and list of As. And in each iteration, we apply n bar in this recursive function. And to run this whole program, we first prepare the list of zeros for this LQ and LA. And then we execute this recursive function. And so we had to measure this AI. So we measure this LQ after running this recursive function. So what we can get is that we could translate the quantum while loop with measurement to the sovereign et al.'s language, which we can say that we can add the line which says, we can add this line. Right, let me summarize our proposal. So we propose a program transformation technique which moves the measurement inside a quantum to the outside. And what we get is that we get physical implementable semantics, and we could found a connection between Yang's work and Abbott work, which is trivial, which is untrivial. And so we have also showed that our technique can also apply to quantum while. For the future work, we want to focus on the special cases in our technique and Abbott et al.'s one. So in our technique, there are some cases that we don't need to introduce dummy values, which is the case which looks like this, which means that we measure the same qubits in den calls and else calls. In that case, we just need to move this same measurement to the outside, which makes no type error. So it means that we don't need to introduce dummy value, which means that our semantics is unique. And there's also a special case in Abbott et al.'s work that in that work that they have observed that in a case the den calls and else calls consist of the same channels, which we can, but we can change the order. And in that case, the semantics is unique. And so we want to think about, we want to observe any relation between these special cases. Yes, so that's the end of my talk, and I appreciate any comments. Yeah, thank you.
All right, thank you very much. Questions?
I have a question because I read the work of that you mentioned about Sabri et al.
Mhm.
I don't remember exactly this work, but what I remember is that in that work, basically they only consider finite recursion because they made recursion on list.
Right, that's right.
Yeah. So I was wondering, how do you want to manage the fact that a quantum while basically could be also unbounded, or you have to put some bounded to make this transformation?
So in that work, yeah, that's true, and they have another limitation that the quantum while loop has to known to be terminate, and it means that we have to prepare. We don't need to. We have to prepare infinite lengths of quantum cube if it's not known to be stopped. I mean, that's true, and yeah, so we can say the same thing for our work. It means that, I mean, so if we don't know if this quantum while terminates, then we have to prepare the infinite lengths of list, infinite list of infinite lengths. But yeah, so we have the same constraints on our work.
All right, so it's like that you basically fix some bound, and the bound is the length of the list of the initial ancillary list basically. You use the ancillary list to fix the bound, the additionally qubit to fix the bound of the loop.
Yes, that's right. That's right, exactly. Thank you.
Yeah, just to make sure I understood it, the technique of the dummy value, this is
Mhm.
basically re-preparing the same state that would have been inside the quantum condition.
No, so we don't know what kind of state this P0 has, so we just need to choose an arbitral state, which makes our semantics arbitral. Does it make sense?
Your semantics are what?
So our semantics also have some kind of parameter, and yeah, as well as Yang's work. Well, but then the original parameter is different, but yeah, we also have a parameter, and we need to choose an arbitral quantum state here. Does it make sense?
Okay, but you're not necessarily having the same semantics as the untransformed program. Is that?
So, I mean, we don't know any semantics for the program transport the before one. So we need to choose to choose a quantum state to define the program, the original program.
Okay, yeah,
thank you.
Yeah, I was also curious about the dots and the 0, 0, 0, because it did seem like it had an M in it.
Mm-hmm.
All right, thank you very much. Ulrich will be talking about a generate and test paradigm for quantum circuits. Okay, take it away.
Hello, my name's Ulrich, and I'll be talking about this DSL that we developed that uses a generate and test paradigm to construct quantum circuits. So generate and test is an idea from classical programming where a naive implementation would generate all possible solutions, then apply some function to all of those solutions and filter those to find the best solution. And we've designed this DSL that, using the same idea, shows that you can use the same underlying classical intuition to understand various common quantum algorithms. So the snippet here is not in the DSL. That's just pseudocode or Haskell to kind of show the idea here. So this is roughly implementing Shor's algorithm to factor the number 15. What you want to do is you generate all possible inputs x, you apply some function, in this case it's a modular exponentiation function, and then you filter the results so that you only get inputs consistent with a particular output. And then the only quantum magic here is this quantum Fourier transform that you apply at the end, and that allows you to then find the period. But our goal is to kind of abstract that away so that you only have to think about these classical steps. So in our DSL, this is all you need to implement the Bernstein-Vazirani algorithm. I'll go through the details, but for now, the important part to note is that the oracle function is implemented as an entirely classical Haskell code for a bitwise dot product. That's annotated with this build oracle keyword to construct a circuit from it. And then to specify the full program, you need three things. You need to specify how many bits are in the input. You need to specify the oracle function from above. And then you need to specify which query you want to apply. So I'm sure most of you are familiar with these algorithms, but these are the four algorithms that we focus on. They are algorithms where there is a known polynomial or exponential speed up over the best, or in the case of Shor's algorithms, the best known classical algorithms. And they all share this property where you're querying some property of an oracle function. So for Deutsch-Josa, you're querying whether the function is constant or balanced. For Bernstein-Vazirani, you are finding the secret bit string where the oracle function is this dot product that we had before. And then for Simon's algorithm, Shor's algorithm, you're finding some kind of period of the oracle function. Now, all of these algorithms have the same structure, and this corresponds nicely to what we saw with the classical generate and test paradigm. So you generate a superposition of all possible inputs, you apply your oracle function, you measure the output register, and this has the effect of filtering your superposition to only get those that are consistent with the measurement result. And then there's this quantum Fourier transform, or for some algorithms, it's an approximate QFT, which is just the Hadamard transform. So the only difference between these algorithms is in the choice of the QFT, whether it's a full QFT or the approximate QFT, and then the initialization of the output register. And so in our DSL, the programmer gets control over this by selecting a query type. So currently we have 3 implemented. Period and bitwise period are respectively for Shor's and Simon's algorithms, which only differ in whether they do the full QFT or the approximate QFT. And then the other 2 algorithms, when you think about it, what you're querying is in fact a subset of the Fourier coefficients of the Fourier expansion for the oracle function, specifically the subset where that set S here is corresponds to singleton sets. And in this case, in both cases, you're using the approximate QFT and setting up the output register to get phase kickback. So our solution is built on Quipper, which, as many of you probably know, is a quantum programming language embedded in Haskell. The points I want to point out here are that it uses the circ monad to capture the effect of building circuits. And then it distinguishes between values that are available only at, or that are available at circuit construction time. These can only be classical, and so they're called classical parameters. And then the values that are available only at circuit execution time are called inputs. They can be classical or quantum. And so you have these families of types. So for Booleans, you have bool, bit, and qubit. And then it also provides other families, for example, for fixed length integers operating mod 2 to the n, you have int m, c int, and qd int. And then Quipper provides this circuit lifting functionality, so you can write classical Haskell code and annotate with this build circuit keyword, and that automatically builds a circuit for you. So this is a slightly modified version of the Bernstein-Vazirani example that I had before. And the build circuit keyword makes that this, in addition to declaring the classical function dot, it also creates this circuit called template dot, where you'll note that all the bools have been replaced by qubits. So it's a useful, although not entirely accurate, mental model to say that classical parameters in this code gets replaced by the corresponding quantum input types. However, you don't always want all your classical parameters to be replaced. For example, for this oracle function, the secret bit string should still be a classical parameter. So Quipper provides some support specifically for bools. They have an ad hoc solution for marking some of them as bool params that are not lifted to qubits. But we developed a more general solution that works for any type. So we have this paramonad. Not shown here are all the type class instances that you'd expect for an identity monad. And it has this family of lift P functions, which in classical code are just equivalent to the lift M family. But within the DSL, they should be considered keywords, because when you prefix a term with one of these lift P functions, then that disables lifting that term into a circuit. And then on top of this, our DSL provides us build oracle, which does the same thing as build circuit, but it also creates this instance of the oracle type, which just encapsulates the classical function together with the quantum circuit, which is important so that we can either simulate it classically or run it as a circuit. And it has the supply param function, which is just function application, and also access the introduction form for the paramonad. And then, as we've seen before, that the final program just specifies these three things. So for a more complete example, here's Shor's algorithm, specifically for factoring now, and then I guess this is the period finding subroutine of it. So you would build a function to find to do modular multiplication, which is the obvious implementation. Then you can use that to build one that does modular exponentiation. It calculates here a to the x mod n. The details aren't really that important. In this case, it's treating the exponent as a bit string and effectively doing exponentiation by squares. And then your full program is specified like this. You say how many bits your inputs are. You have your oracle function, apply the parameters to it, and then say you want the period. So our DSL, we have an implementation that can convert these programs into Quipper circuits. And we've tested all four of the algorithms that I mentioned before, just via simulation. I gave some qubit and gate counts here. You'll note that they are quite high. So using the Bernstein-Vazirani algorithm with 4 bits requires 18 qubits and 34 gates, and then Shor's algorithm, just a factor 15, requires almost 400 qubits and 60,000 gates. However, there's still some obvious opportunities for optimization here. Here I'm showing the circuit generated for the Bernstein-Vazirani algorithm. And you'll note that these 3 ancilla qubits are effectively useless. They are initialized to classical values and just used to access those constants. So the one is just 0, and then 2 of them are initialized to the secret bit string. And so the missed opportunity here is that with our annotations of this paramonad, you know which operands of an operator have a effectively a constant value when the circuit is constructed. And so using that, it should be possible to automatically select more optimized implementations of the operations. And I believe that this is also the largest problem with the Shor's algorithm example, which is using a naive implementation of multiplication, which assumes that both inputs are quantum values. And so yeah, this project is a work in progress. As I said, there's still some obvious optimizations to do. We'd like to identify other common idioms from other algorithms that we can implement. An obvious example is Grover's algorithm, which is also definitely something which queries a particular property of an oracle function, and it would be pretty straightforward to add to the DSL as well. And then there's still some implementation work to be done, like the classical simulation without building a circuit first, and post-processing for some of these algorithms. So just to summarize, our first contribution here was the extension of Quipper with the scheme to distinguish these classical values that we do want to be lifted into quantum types from those that we don't. Then we implemented this DSL that allows one to write quantum programs for specific algorithms by only implementing a classical oracle function and specifying what query to perform. And then we believe that this demonstrates that there's a sort of classical intuition that is in fact sufficient to express some common quantum algorithms. I want to thank Amir Sabri, who's guided me throughout this project. The source code is available there. You may want to wait until tonight so that I can just go and get a nice README ready. Thanks for your attention.
Thank you, Ulrich. I'm awaiting that README so I can download this and play with it. Questions?
So the paradigms generate and test is less general than just having oracles. A lot of algorithms which use oracles which are not of this form. So what's the prospects of extending this to a bigger class of things?
So we have some ideas. Nothing very concrete yet. And now that you mention it, maybe if we do end up extending it in that way, the name is no longer that appropriate. But so we have some ideas that you can find other algorithms that would kind of fit the same pattern and perhaps prove that there are larger classes of algorithms that do it by so if we look at, let's say, decompositions of algorithms into Toffleys and Hadamards and rotations, then if you can find some circuit identities that effectively allow you to commute things, doesn't have to be a plain commutation. They could change phases and stuff, but so that you can kind of get things into the same form where you have, say, Hadamards on the one side and Hadamards or a QFT on the other side. I think that's a promising direction that I'd like to look into.
So you mentioned that the circuits generated are often very inefficient. They have a lot of extra qubits. There are many people in this audience who have existing circuit optimizers. Have you tried just throwing the output circuits into any of these and seeing if it sort of solves the problem?
Not yet, but that's a very good idea.
All right.
Yeah, I think, as I said, some of it is very obvious inefficiencies, like those extra ancilla qubits that it allocates and just gives them a constant value. So I think a lot of optimizers will probably be able to do a good job with those, but I haven't tried anything.
Yeah, it's a good question because some of them don't do the naive stuff; they only do the smart stuff. So I found that it's not always like sometimes there's this really obvious opportunities for optimization that they don't get. So it would be an interesting study. Any other questions? All right, let's thank our work again. And I think that's it. Mathis, do you want to have any closing words?